Hello there and welcome back to the Science Sleepy Minds. Tonight, picture yourself standing in absolute darkness, the kind of darkness that has weight to it, that presses against your eyelids like velvet. Now imagine a single golden hexagon catching the faintest glimmer of light from 13 billion years away. That glimmer has been travelling since before the Earth existed, before the Sun ignited, before our entire galaxy finished assembling itself from clouds of primordial dust. And somewhere out there, parked at a lonely point in space 1,000,000 miles from your pillow, a telescope the size of a tennis court is collecting that ancient glow and turning it into data that has made some of the smartest people on this planet lose sleep. Ironically, you are here to gain sleep, so you probably will not survive this journey awake, and honestly, that is perfectly fine. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment with your location and local time. I always love seeing who is tuning in from Sao Paulo at 2 in the morning or from a tiny flat in Oslo at midnight. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You are floating. Not metaphorically, not poetically, but in the most literal sense your imagination will allow. You're suspended at a point in space called the second Lagrange point, roughly 1.5 million kilometers from Earth, where the gravitational tug of the Sun and the gravitational tug of our home planet reach a kind of lazy truce. It is quiet here, in a way that no library, no remote cabin, no bottom of the ocean trench could ever replicate. The silence is not the absence of sound. It is the absence of medium. There is nothing here for sound to travel through, nothing but the cold vacuum and the faintest hiss of cosmic microwave background radiation, which is really just the universe's baby photo still echoing after nearly 14 billion years, and hovering in this void, spinning so slowly you would never notice, is the James Webb Space Telescope. You've probably seen pictures. It looks like a giant golden honeycomb mounted on a silver kite. The honeycomb is actually 18 hexagonal mirror segments, each about 1.3 meters across, each coated in a layer of gold so thin that if you gathered all of it together, you would have roughly enough to fill a marble. Gold, as it turns out, is exceptionally good at reflecting infrared light, and infrared light is the language that the oldest objects in the universe speak. Visible light from the earliest stars and galaxies has been stretched by the expansion of space itself, pulled like taffy until it slides off the red end of the visible spectrum and into the infrared. Your eyes cannot see it. The Hubble Space Telescope, bless its aging heart, could only catch a fraction of it. But Webb was designed from the ground up to listen to this specific whisper. The sunshield beneath those mirrors is the size of a tennis court, 5 layers of a material called capton, each thinner than a human hair, each separated by a vacuum gap. The sun-facing side of that shield can reach temperatures of about 85 degrees Celsius, hot enough to make you deeply regret touching it, while the shadow side plunges to minus 233 degrees Celsius. That temperature difference exists across a gap you could practically reach your arms across. Engineers sometimes describe it as having summer and deep space winter, separated by the width of a dining table, which is the kind of sentence that makes you quietly set down your coffee and reconsider everything you know about insulation. Now here is the thing that sets the mood for tonight. When scientists build a telescope this powerful, they expect surprises. That is the entire point. You do not spend $10 billion and 25 years of engineering headaches to confirm what you already know. You do it to peek behind the curtain. But there is a difference between a pleasant surprise like finding an extra fry at the bottom of the bag and a deeply unsettling surprise like discovering that the bag has no bottom at all and the fries extend into a dimension you cannot comprehend. What Webb has been finding since it opened its golden eyes in mid-2022 falls rather firmly into the second category. Historians of science often point out that every great observatory has broken something. When Galileo pointed his crude refractor at Jupiter in 1610, he shattered the idea that everything orbited Earth. When Edwin Hubble used the Hooker telescope on Mount Wilson in the 1920s, he broke the notion that the Milky Way was the entire universe. Scholars still argue whether these paradigm shifts happen in sudden revolutions or slow, grinding accumulations of uncomfortable evidence, a debate that the philosopher Thomas Kuhn made famous and that academics have been bickering about ever since, which is really just what academics do for fun. Webb appears to be staging its own revolution, and the uncomfortable evidence is piling up faster than anyone anticipated. What scientists were afraid of in the broadest sense was being wrong. Not wrong about a detail or a decimal place, but wrong about the scaffolding, wrong about the fundamental story of how the universe went from a hot, dense, featureless soup to the structured, galaxy-filled, bewilderingly complex place you currently inhabit while trying to fall asleep. The standard model of cosmology, affectionately called Lambda CDM, has been the reigning champion for more than 2 decades. It describes a universe dominated by dark energy and cold dark matter, where galaxies form slowly and hierarchically, small clumps merging into bigger clumps over billions of years like cosmic snowballs rolling downhill. It is elegant, it is well tested, and Webb is poking holes in it with the enthusiasm of a toddler discovering bubble wrap. In the sections ahead, you're going to drift through those holes one by one. You will visit galaxies that have no business being as large and as polished as they are at such a young cosmic age. You will meet black holes so massive and so ancient that the math simply does not have room for them. You will squint at the atmospheres of alien worlds and feel the strange chill of realizing that some of those worlds may be as barren as a parking lot at 3 a.m, and you will sit with the quiet, almost philosophical dread that comes from understanding that the universe may not be headed where we thought it was headed. But all of that unfolds gently, one piece at a time, like a bedtime story told by the cosmos itself. So settle in, let the hum of your fan fill the gaps between sentences, and let your eyelids do whatever they want, because the light Webb is collecting tonight has waited billions of years to reach you, and it will not mind if you close your eyes along the way. The story begins, as most good space stories do, with an idea that was slightly too ambitious, a budget that was wildly too optimistic, and a group of scientists who simply refused to let the universe keep its secrets. The idea that became the James Webb Space Telescope did not arrive in a burst of inspiration. It crawled into existence during a workshop in 1996, hosted at the Space Telescope Science Institute in Baltimore, where a group of astronomers sat around and asked a deceptively simple question: what comes after Hubble? At the time, Hubble was barely 6 years into its corrected mission, having famously launched in 1990 with a mirror that was ground to the wrong shape, a $2 billion pair of glasses with the wrong prescription. NASA had sent astronauts up to fit it with corrective optics in 1993, and by 1996 it was finally delivering the jaw-dropping images that would make it a household name. So asking what comes next felt a bit like asking what comes after dessert while you're still chewing. But astronomers are a forward-looking species, and they knew that Hubble, for all its brilliance, was fundamentally blind to the infrared universe. You need to understand why infrared matters, because it is the entire reason Webb exists, and the entire reason it found what it found. Visible light is a narrow little sliver of the electromagnetic spectrum, the cosmic equivalent of being able to hear only the middle C on a piano while an entire orchestra is playing. Infrared sits just below visible red, and it carries information that visible light simply cannot. It passes through dust clouds that block optical telescopes. It reveals the heat signatures of cool objects like forming planets and distant brown dwarfs. And crucially, it catches the light of the most ancient objects in the universe, light that started as ultraviolet or visible, but has been redshifted by the expansion of space into the infrared band. If you want to see the universe as it was in its infancy, you have to look in infrared. There is no shortcut, no workaround, no clever hack. You build an infrared telescope or you stay ignorant. The astronomers at that 1996 workshop called their dream the Next Generation Space Telescope, a name that carried all the gravitas of a science fiction spin-off. The plan was bold, but in theory straightforward. Build a telescope with a primary mirror at least 6 meters across, far larger than Hubble's 2.4 meters, equip it with infrared instruments, and park it far from Earth, where the planet's own heat would not contaminate the readings. The estimated cost was about $1 billion, and the launch was penciled in for somewhere between 2007 and 2011. If you're doing the math and feeling a twinge of dark amusement, you're right to feel it. The final cost ballooned to roughly $10 billion, and the telescope did not launch until December 2021, a delay so spectacular that it became a running joke in the astrophysics community. There is a quirky little factoid buried in NASA budget archives, showing that the project was nearly cancelled at least 4 separate times, surviving each near-death experience through a combination of political lobbying, scientific passion, and what one frustrated congressman reportedly called sheer bureaucratic stubbornness. The telescope was renamed in 2002 after James E. Webb, who served as NASA's administrator during the Mercury and Gemini programs and through most of the Apollo build-up. Webb was not a scientist. He was an administrator, a political operator, a man who understood that getting to the moon required not just rocket fuel, but congressional fuel. The naming choice was not without controversy. Some astronomers felt the telescope should honour a scientist, not a bureaucrat. Others later raised concerns about Webb's possible involvement in the federal government's lavender scare policies of the 1950s, which targeted gay and lesbian employees. NASA conducted a review and kept the name, but historians still argue whether the investigation was thorough enough or whether the agency simply wanted to avoid the headache of renaming a project that was already years behind schedule. Either way, the name stuck and the telescope carried it into orbit. Building Webb was an exercise in engineering masochism. The primary mirror, those 18 golden hexagons you picture whenever someone mentions the telescope, could not launch in one piece because no existing rocket fairing was wide enough. So the mirror was designed to fold, origami style, and unfurl after reaching space. Each segment had to be polished to a precision of about 25 nanometers, which is roughly 1,000th the width of a human hair. If you scaled one of those mirror segments up to the size of the continental United States, the largest bump on its surface would be about 2 inches tall. That is the level of smoothness we're talking about, the kind of precision that makes you wonder how humans managed to lose socks in the laundry, yet somehow pull this off. The instruments mounted behind that mirror are marvels in their own right. NIRCam, the near-infrared camera, serves as Webb's primary imager, and was the tool responsible for those first breathtaking deep-field photographs. NIRSpec, the near-infrared spectrograph, can analyse the light of up to 100 objects simultaneously, splitting their glow into spectral fingerprints that reveal chemical composition, temperature, density, and motion. MIRI, the mid-infrared instrument, peers even deeper into the infrared and operates at a staggering minus 266 degrees Celsius, just 7 degrees above absolute zero, which is colder than any natural environment in the entire solar system. And then there is FGSNIRISS, the the fine guidance sensor, a near-infrared imager, and slitless spectrograph, built by the Canadian Space Agency, whose job is to keep the telescope pointed with absurd accuracy. Webb can lock onto a target and hold steady enough to focus on a single grain of sand from kilometers away. If your hand were that steady, you would be the most terrifying surgeon on the planet. The European Space Agency contributed the Ariane 5 rocket that launched Webb, and here is a detail that still makes engineers smile with disbelief. The Ariane 5 delivered Webb on such a precise trajectory that the telescope used significantly less fuel for course corrections than planned. That extra fuel effectively doubled Webb's operational lifespan from the original 10-year estimate to potentially 20 years or more. One good rocket launch, one stroke of navigational luck, and suddenly humanity has twice as long to stare into the abyss before the abyss politely asks us to stop. All of this effort, all of this money, all of these years of testing and retesting and redesigning and arguing in conference rooms with stale coffee was aimed at one goal: seeing farther and more clearly into the infrared universe than any instrument before. Scientists knew they would find something. They hoped they would find clarity. What they were not entirely prepared for was the possibility that clarity would arrive in the form of contradiction, that the sharpest eyes humanity had ever built would look into the deep past and see a universe that did not match the story they had been telling themselves for decades. But before any of that could happen, the telescope had to survive its launch and its deployment, and that process alone was enough to turn every astrophysicist on Earth into a nervous wreck for 2 solid weeks. Christmas morning, 2021. While most of the world was unwrapping gifts and negotiating the politics of family seating arrangements, a group of scientists and engineers gathered at the European Space Agency's launch facility in Kourou, French Guiana, staring at screens with the kind of focused dread usually reserved for people defusing explosives. The Ariane 5 rocket sat on the pad, and nestled inside its fairing, folded up like the most expensive piece of origami ever constructed, was the James Webb Space Telescope. 25 years of work, $10 billion, and now the whole thing was strapped to a controlled explosion pointed at the sky. You have to appreciate the peculiar cruelty of rocket launches. There is no partial credit. You either succeed completely, or you produce the most expensive firework in human history. The Ariane 5 had a strong track record, but strong is not perfect, and Webb was not the kind of payload you could simply rebuild and try again. There was no backup Webb sitting in a warehouse somewhere. This was it. One shot. The countdown ticked to 0. The solid rocket boosters ignited, and the vehicle climbed into the tropical sky above the Atlantic, trailing a column of white-hot exhaust that lit up the morning like a second sunrise. Inside mission control, people cried, some from relief, some from sheer nervous overload, and at least a few because they had been holding their breath for so long they were mildly oxygen deprived. But the launch, terrifying as it was, turned out to be the easy part. What followed over the next 29 days was a sequence of mechanical deployments so complex and so fragile that engineers had identified 344 individual points of failure. 344 moments where one stuck latch, one jammed motor, one improperly tensioned cable could turn the most sophisticated space observatory ever built into a $10 billion piece of space debris. To put that in perspective, the Apollo missions had nowhere near that many single points of failure during their most critical phases. Historians like to compare it to the moon landings in terms of ambition, but in terms of pure mechanical anxiety, Webb may have been in a category all its own. The first major deployment began about 30 minutes after launch, when the solar array unfolded to start generating power. That went smoothly. Then came the high-gain antenna, which would serve as Webb's communication link back to Earth. Also smooth. But these were the appetizers. The main course was the sunshield, and the sunshield was where the nightmares lived. Picture this. You have 5 layers of Kapton, a polyimide film that is extraordinarily thin, extraordinarily delicate, and extraordinarily important. Each layer is about the thickness of a human hair. Together, they form a barrier that protects the telescope's instruments from the sun's heat, the Earth's heat, and even the heat of the moon. Without the sunshield, the infrared detectors would be blinded by thermal noise, like trying to listen to a whisper at a rock concert. The shield had to deploy perfectly, stretching taut across a framework of booms and cables, each layer separating from the next by precise gaps that create a cascading thermal gradient. This sun-facing layer absorbs the brunt of the heat, and each subsequent layer radiates less and less until the final layer, facing the telescope, sits at that astonishing -233 degrees Celsius. The deployment of this sunshield took about 5 days and involved 140 individual release mechanisms, 70 hinge assemblies, 400 pulleys, and roughly 90 cables totaling over a quarter-mile in length. There is a quirky engineering detail that rarely makes it into the headlines. During ground testing, the team discovered that the Kapton layers had a tendency to stick together, not because of any adhesive, but because of simple surface interaction at the molecular level. In the vacuum of space, where there is no air to provide a cushion between surfaces, this sticking tendency could have been catastrophic. The solution involved special coatings and meticulous folding patterns designed to ensure each layer peeled apart cleanly. Engineers tested this process repeatedly on Earth, but there is a well-known problem in space engineering. You cannot perfectly simulate zero gravity, vacuum, and extreme temperature simultaneously in any ground facility. At some point, you simply have to trust your math and your manufacturing and watch. Mission Control watched. The world watched. Astrophysicists who had spent entire careers waiting for this telescope watched from their living rooms, their offices, their phones, propped against coffee mugs in faculty lounges. Day by day, the sunshield unfolded. The pallets that held it lowered away from the telescope body. The booms extended, pulling the membranes outward. The tensioning mechanisms activated, stretching each layer into its final shape. Every step was confirmed by telemetry, and every confirmation was met with applause that sounded less like celebration and more like the exhale of people who had genuinely considered the possibility that it might not work. After the sunshield came the secondary mirror, a small round mirror mounted on the end of 3 long struts that had been folded flat for launch. This mirror is the first surface that incoming light hits after reflecting off the primary mirror segments, and its position has to be accurate to within a fraction of a millimeter. The struts deployed without incident, clicking into place with a mechanical certainty that engineers later described as one of the most satisfying sounds they had ever heard transmitted through telemetry data, which is an incredibly nerdy sentence but also an entirely understandable one. Then came the primary mirror wings. The 18 hexagonal segments were arranged in a central section, with 2 folding wings, 3 segments on each side. These wings had to rotate into position and lock with enough precision that the entire mirror surface could later be aligned into a single, optically perfect collecting area. The first wing deployed on January 7th. The second followed on January 8th, and with that final click, the James Webb Space Telescope was fully open, fully deployed, and coasting toward its orbital home at the second Lagrange point. The alignment process that followed was its own quiet miracle. Each of the 18 mirror segments had 7 actuators, tiny motors that could adjust the segment's position and curvature with nanometer precision. Over the course of several weeks, the team used a relatively bright, isolated star called HD 84406 as a reference point. Initially, each segment produced its own separate image of the star, resulting in 18 blurry dots scattered across NIRCam's detector. Slowly, painstakingly, the actuators nudged each segment until all 18 dots converged into a single, sharp, blazing point of light. Scientists still argue whether this alignment phase was more nerve-wracking than the sunshield deployment. The sunshield was dramatic, mechanical, and pass-fail. The alignment was subtle, iterative, and demanded patience that bordered on the monastic. Both could have ended the mission. Both did not. By late June of 2022, Webb was fully calibrated and ready to observe. The telescope that had nearly been cancelled 4 times, that had survived every congressional budget review, every engineering setback, every pandemic-related delay, was finally doing what it was built to do. It was staring into the infrared darkness with those 18 golden eyes, and the darkness was staring back with a message that nobody quite expected. The first image arrived on July 11th, 2022, one day ahead of the official public release, delivered in a brief ceremony at the White House by President Biden. You might remember where you were when you saw it. Or you might have scrolled past it on social media between a meme and a sandwich photo, which is honestly a very 21st century way to encounter the deepest image of the universe ever taken. Either way, the image was extraordinary, and what it contained was already beginning to unravel the neat narrative that cosmologists had spent decades constructing. The target was a patch of sky called SMACS 0723, a galaxy cluster located about 4.6 billion light-years from Earth. Galaxy clusters are the heaviest gravitationally bound structures in the universe, enormous collections of hundreds or thousands of galaxies held together by dark matter and filled with superheated gas that glows in X-rays. But the cluster itself was not the main attraction. The cluster was the lens. Its combined mass was so enormous that it warped the fabric of space-time around it, bending and magnifying the light of far more distant galaxies behind it, galaxies that would otherwise be too faint and too far away to see. This effect is called gravitational lensing, and Einstein predicted it over a century ago, though he reportedly doubted anyone would ever observe it directly. Historians still argue whether Einstein's skepticism was genuine humility or a kind of intellectual coyness, since the man had a well-documented habit of being right about things he claimed to be uncertain about. What Webb revealed in that tiny patch of sky, a patch you could cover with a grain of sand held at arm's length, was staggering. Thousands of galaxies, not hundreds, thousands. Spirals, ellipticals, irregulars, smeared arcs of gravitationally lensed light, each arc a distant galaxy, stretched and distorted by the cluster's gravitational field into shapes that looked almost like brushstrokes on a dark canvas. Some of these galaxies were relatively nearby, cosmically speaking, only a few billion light-years away, but others were much, much farther. Their light had been travelling for over 13 billion years, meaning Webb was seeing them as they existed when the universe was less than 1 billion years old. You are essentially looking at baby pictures, except the babies are entire galaxies, and the photo album is made of warped space-time and infrared photons. Now here is where the trouble started, and where you should probably sink a little deeper into your pillow, because this is the part that made astrophysicists start sending each other slightly panicked emails. Among those ancient distant galaxies, several stood out. They were too bright, too structured, too massive. In the standard model of cosmology, galaxies in the very early universe should look like messy, small, irregular blobs. They should be the cosmic equivalent of rough drafts, collections of gas and young stars still figuring out how to organise themselves. What Webb saw instead were galaxies that appeared remarkably mature, with well-defined shapes, significant stellar populations, and masses that rivaled or even exceeded the Milky Way. and they existed at a time when the universe was barely 5% of its current age. Imagine walking into a nursery and finding a fully grown adult sitting in one of the cribs, reading the Financial Times and complaining about interest rates. That is roughly the level of conceptual disruption these galaxies represent. They should not be there, not at that size, not at that age, not with that level of structural sophistication. And yet there they were, glowing calmly in the infrared, completely unbothered by the theoretical crisis they were causing. The scientific community responded with a mixture of excitement and anxiety that is hard to overstate. Within weeks of the first data release, preprint servers were flooded with papers. Some researchers tried to explain the massive early galaxies within the existing framework, proposing that star formation in the early universe might have been far more efficient than previously modelled. Others suggested that the galaxies might not be as massive as they appeared, that certain calibration issues or dust effects could be inflating the mass estimates. And a smaller, bolder group began whispering that maybe, just maybe, the standard cosmological model needed more than a minor adjustment. Maybe it needed a fundamental rethink. One of the first major papers to sound the alarm came from a team led by Ivo Labbé at the Swinburne University of Technology in Australia. Using Webb's NearCam data, the team identified several galaxy candidates at redshifts above 7, meaning their light had been travelling for over 13 billion years. The estimated masses of these galaxies were enormous, some reaching tens of billions of solar masses. For context, the Milky Way has a stellar mass of roughly 50 to 60 billion solar masses, and it took over 13 billion years to accumulate that. These candidate galaxies appeared to have assembled a significant fraction of that mass in under 700 million years. The paper's tone was measured, as scientific papers tend to be, but the implications screamed from between the lines. If these mass estimates held up, something was very wrong with the timeline. A quirky detail that emerged during this early frenzy of analysis involved the colours of these ancient galaxies. In astronomy, colour is a proxy for age and composition. Older stellar populations tend to be redder because their hot blue stars have already burned out, leaving behind cooler, longer-lived red stars. Several of Webb's early galaxy candidates displayed colours consistent with mature stellar populations, which added another layer of impossibility to the puzzle. It was not just that these galaxies were massive. They appeared to contain old stars, stars that would have needed hundreds of millions of years to evolve to that stage, compressed into a cosmic window that barely left room for the stars to have formed at all. It is the kind of finding that makes you want to check the telescope's prescription, except Webb's optics had been verified to be the most precise ever flown. Not everyone was convinced, of course. Science thrives on skepticism, and several groups quickly published rebuttals arguing that spectroscopic confirmation was needed before anyone should start rewriting textbooks. Photometric estimates, which rely on the brightness of galaxies and different filters, can be fooled by dusty interlopers at lower redshifts masquerading as high redshift objects. The astronomical community collectively held its breath and waited for the spectroscopic follow-up, the equivalent of checking someone's identification after they have made an extraordinary claim at the door. And when that follow-up arrived over the following months, the results were a complicated mixture of vindication and surprise that only deepened the mystery, pulling cosmology further into territory that felt genuinely uncharted. The spectroscopic confirmations began rolling in through late 2022 and into 2023, and they landed on the astrophysics community like a series of polite but devastating punches. Remember those galaxy candidates that Ivo Labbé's team and others had identified using photometric data? The ones that looked impossibly massive and impossibly early? Some of them turned out to be exactly what the skeptics had warned about. Lower redshift galaxies cloaked in dust that mimicked the colours of truly ancient objects. That was expected. That was the system working as designed. The scientific method doing its slow, methodical janitorial work. But a significant number of those candidates survived the spectroscopic gauntlet. Their redshifts were confirmed, their distances were real, and their implications were not going away. One of the most striking confirmed objects was a galaxy designated JADES-GS-Z13-0, detected by the JWST Advanced Deep Extragalactic Survey. Spectroscopic analysis placed it at a redshift of approximately 13.2, meaning its light left when the universe was only about 320 million years old. 320 million years. That sounds like a long time if you're thinking in terms of human history, but in cosmic terms it is barely a blink. The universe at that age was still emerging from a period called the Cosmic Dark Ages, the epoch after the cosmic microwave background was released but before the first stars and galaxies had fully lit up the void. Finding a galaxy at this redshift is like finding a lit candle in a room where someone only just struck the match. The candle should not be there yet. The wax should not have had time to form, let alone catch a flame. But JADES-GS-Z13-0, while astonishingly distant, was not the real headache. It was relatively small and faint, consistent with the kind of nascent proto-galaxy you might expect in the very early universe. The real headache came from galaxies at slightly lower redshifts between 7 and 10, corresponding to a universe roughly 500 to 700 million years old. These galaxies were confirmed to be genuinely massive, with stellar masses that pushed into the billions of solar masses. They were not small, tentative structures. They were robust, luminous, and in some cases showed evidence of having already begun to wind down their star formation, as if they had burned through their gas supply in a frenzy and were now settling into a quiet retirement. Astronomers sometimes refer to these as quenched galaxies, which sounds peaceful, but is actually a term loaded with confusion, because nobody could adequately explain how a galaxy could form that many stars and then stop that quickly in the time available. You're lying there perhaps with your eyes half closed, and this might feel like an abstract numbers game, redshifts and solar masses and formation timescales, so let you put it in more tangible terms. The standard model of cosmology, lambda CDM, predicts that the universe built its galaxies the way you might build a snowman. You start with a small ball, roll it around, and it gradually picks up more material. Small dark matter, halos, formed first, attracted gas, formed modest clumps of stars, and those clumps merged over billions of years into the majestic spirals and giant ellipticals you see in the modern universe. This hierarchical assembly model has been the backbone of galaxy formation theory since the 1980s, supported by computer simulations that can track the growth of cosmic structure from the Big Bang to the present day. These simulations are impressive. They run on supercomputers for months, modelling the gravitational dance of billions of particles, and they produce virtual universes that look reassuringly similar to the one you actually live in. The problem is that when you compare those simulated universes to what Webb is actually seeing in the early cosmos, the agreement starts to crack. The simulations predicted that galaxies at redshift 8 or 9 should max out at roughly 1 billion solar masses, maybe 2 billion if you pushed the models and allowed for some optimistic assumptions about star formation efficiency. What Webb found were galaxies at those same redshifts with 5, 10, sometimes estimates approaching 50 billion solar masses. The mismatch is not subtle. It is not a rounding error. It is the difference between predicting a house cat and finding a tiger in your kitchen, except the tiger is also somehow older than it should be, and already retired from hunting. Several explanations have been floated, each with its own strengths and its own uncomfortable compromises. The most conservative explanation is that star formation in the early universe was simply more efficient than anyone modelled. In the standard picture, only a small fraction of available gas in a dark matter halo actually condenses into stars. Most of it is heated by radiation, blown away by supernovae, or otherwise prevented from collapsing. If that efficiency was significantly higher in the early universe, perhaps because the gas was denser, cooler, or less enriched with heavy elements that aid in radiating energy away, then you could plausibly build bigger galaxies faster. This explanation has the appeal of not requiring any changes to fundamental physics, just a recalibration of astrophysical processes. But it raises its own questions. If star formation was that efficient early on, why did it slow down later? What mechanism pumped the brakes, and why do the simulations, which have been tuned against decades of observations, not already account for this? A more radical explanation involves the nature of dark matter itself. Lambda CDM assumes cold dark matter, particles that move slowly and clump readily, forming the gravitational scaffolding on which galaxies are built. But what if dark matter is not perfectly cold? What if it has properties, self-interactions, or a slight warmth that alter the way halos form in the early universe? Some physicists have proposed that a different flavour of dark matter could produce more massive halos earlier, providing the gravitational wells needed to assemble giant galaxies on an accelerated timeline. This is speculative territory, the kind of idea that gets published with a lot of caveats and conditional language, but it is gaining traction precisely because the observational pressure from Webb is becoming difficult to ignore. And then there is the truly unsettling possibility, the one that keeps theoretical cosmologists awake despite their best efforts to remain measured. Perhaps the issue is not with the astrophysics at all. Perhaps the issue is with the cosmology. Perhaps the parameters of the lambda CDM model, the density of dark matter, the properties of dark energy, the initial conditions set by cosmic inflation need more than fine-tuning. Perhaps they need revision. This is the door that nobody particularly wants to open, because behind it lies the prospect of rebuilding the standard model of cosmology from scratch, a task roughly as appealing as renovating a house while you're still living in it during a rainstorm. But Webb keeps knocking on that door with every new data release, and the knocking is getting louder. Scholars still argue whether the current tension represents a true crisis or merely a period of productive discomfort, the kind that historically precedes major advances. The optimists call it growing pains, the pessimists call it a reckoning, and the telescope, indifferent to human anxiety, keeps collecting light. So you have these galaxies sitting in the early universe like skyscrapers in a Stone Age village, and the question gnawing at every cosmologist's brain is whether the village's blueprint was wrong all along. To understand why that question carries so much weight, you need to spend a moment inside the blueprint itself, the lambda CDM model, and appreciate just how much modern astrophysics is built on its foundations. Because if those foundations shift, everything built on top of them shifts too, and that is a lot of everything. Lambda CDM stands for lambda cold dark matter. Lambda refers to the cosmological constant, a term Einstein originally introduced into his equations of general relativity to keep the universe static, which was the fashionable assumption in 1917. When Edwin Hubble discovered that the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder, though historians still argue whether he actually used that exact phrase or whether it was embellished by his colleague George Gamow years later. Either way, the cosmological constant was shelved for decades, treated as a mathematical curiosity with no physical relevance. Then, in 1998, two independent teams studying distant Type 1a supernovae discovered that the expansion of the universe was not just continuing but accelerating. Something was pushing the cosmos apart faster and faster, and the simplest mathematical description of that something turned out to be Einstein's old cosmological constant, resurrected from the dustbin and given a new identity: dark energy. Dark energy is, to put it gently, one of the most embarrassing mysteries in all of physics. It constitutes roughly 68% of the total energy content of the universe. It dominates the cosmic budget. And nobody knows what it is. The cosmological constant interpretation treats it as an intrinsic property of space itself, a fixed energy density that pervades every cubic centimetre of the vacuum. Quantum field theory predicts that the vacuum should indeed have energy, but when physicists calculate how much, they get a number that is roughly 120 orders of magnitude larger than the observed value. That is not a small discrepancy. That is the worst prediction in the history of science, a mismatch so colossal that it has its own name, the cosmological constant problem, and its own cottage industry of theoretical attempts to resolve it, none of which have succeeded to anyone's full satisfaction. The CDM part of the name refers to cold dark matter, and here you encounter the other enormous gap in human understanding. Dark matter makes up about 27% of the universe's energy budget. It does not emit light, absorb light, or interact with light in any detectable way. You cannot see it, touch it, or bottle it. Its existence is inferred entirely from its gravitational effects. Galaxies rotate faster than they should based on their visible mass alone. Galaxy clusters are more massive than their luminous content accounts for. The cosmic microwave background has a pattern of temperature fluctuations that only makes sense if a substantial amount of invisible matter was present in the early universe, tugging on the primordial plasma and sculpting the seeds of future cosmic structure. The cold in cold dark matter refers to the velocity of the particles. In the standard picture, dark matter particles move slowly compared to the speed of light, which means they clump easily under gravity. This clumping is essential. It provides the gravitational scaffolding on which ordinary matter, the protons and neutrons and electrons that make up you and your pillow and your planet, can accumulate and eventually form stars, galaxies, and everything else. Without cold dark matter, the universe after the Big Bang would have remained a featureless, lukewarm soup of radiation and gas. The tiny density fluctuations imprinted during cosmic inflation would have had nothing to amplify them. Structure would not have formed. You would not exist. Your pillow would not exist. It is a sobering thought, and also a convenient excuse to hug your pillow a little tighter. Lambda CDM combines these two mysterious ingredients with well-established physics, general relativity, the known properties of ordinary matter, and the initial conditions from the cosmic microwave background to produce a model of cosmic evolution. That model has been spectacularly successful. It correctly predicts the large-scale distribution of galaxies, the statistical properties of the cosmic microwave background to exquisite precision, the abundance of light elements forged in the first few minutes after the Big Bang, and the way gravitational lensing distorts the images of distant objects. For 2 decades, Lambda CDM has passed almost every observational test thrown at it. It is the standard model for good reason. It works, but working is not the same as being complete, and this is where you start to feel the floor creak beneath you. Lambda CDM is a framework, not a fundamental theory. It describes what the universe does without fully explaining why. It tells you that dark energy behaves like a cosmological constant, but does not tell you what dark energy actually is. It tells you that dark matter is cold and collisionless, but does not tell you what particle it consists of, despite decades of increasingly sensitive experiments that have searched for dark matter particles and found nothing. It is a model that fits the data beautifully while leaving the two largest components of the universe essentially unexplained, which is a bit like having a recipe that produces a perfect cake, even though you have no idea what 2/3 of the ingredients are. And now Webb is stress testing this model in a regime it was never directly calibrated against, the very early universe. Lambda CDM was built and tuned using observations of the relatively nearby cosmos and the cosmic microwave background, which represents the universe at an age of about 380,000 years. The epoch between that ancient snapshot and the first billion years or so has been largely terra incognita, a gap in the observational record that theorists filled with simulations and educated guesses. Webb is now flooding that gap with actual data, and the data is not cooperating. There is a wonderfully nerdy analogy that circulated on astrophysics Twitter during the early months of Webb's operation. Someone compared Lambda CDM to a GPS system that works perfectly in the city, but starts giving bizarre directions the moment you drive into the countryside. The roads it predicts do not match the roads that exist. The destinations it calculates are in the wrong places. The estimated arrival times are off by hours. The GPS is not broken in any obvious way. It still calculates routes. It still shows a map. But the map no longer matches the territory, and the further you drive, the worse the mismatch becomes. You can feel the gentle unease in that analogy, and you should, because what comes next only deepens it. The impossible early galaxies were just the first crack. Webb was simultaneously sharpening a different tension, one that had been simmering for nearly a decade before the telescope even launched. A disagreement so persistent and so stubborn that cosmologists had given it a name that sounds almost clinical, but carries a faint whiff of dread. The disagreement is called the Hubble tension, and it has been quietly driving cosmologists towards something resembling an existential crisis since about 2014. The name sounds deceptively mild, like a headache you could fix with aspirin and a nap, but the reality is far more disorienting. At its core, the Hubble tension is a simple problem with no simple solution. Two different methods of measuring how fast the universe is expanding give two different answers, and those answers refuse to converge no matter how many times the measurements are repeated, refined, and triple-checked. The expansion rate of the universe is described by a number called the Hubble constant, denoted h0, which tells you how fast a galaxy at a given distance is receding from you. A higher value means the universe is expanding faster. A lower value means slower. Measuring this number has been one of the great quests of observational cosmology, stretching back to Edwin Hubble himself, who in 1929 published the first evidence that distant galaxies were moving away from us at velocities proportional to their distances. His original estimate of the expansion rate was wildly off by modern standards, roughly 500 kilometers per second per megaparsec, which would have made the universe embarrassingly younger than some of its own stars. Over the following decades, astronomers painstakingly refined the measurement, correcting for errors in distance calibration, and the value gradually settled into a much more reasonable range. But settling into a range is not the same as settling on a number, and that distinction is where the tension lives. One method of measuring h0 is called the distance ladder. It's exactly what it sounds like, a series of stepping stones that carry you from nearby objects, whose distances you can measure directly to increasingly distant objects, whose distances you infer from the previous rung. The first rung uses parallax, the apparent shift in a star's position, as Earth moves from one side of its orbit to the other. This works beautifully for stars within a few thousand light years. The next rung uses Cepheid variable stars, pulsating giants whose intrinsic brightness is directly related to the period of their pulsation, find a Cepheid, measure its pulsation period, and you know how bright it truly is. Compare that to how bright it appears and you can calculate its distance. Henrietta Swan Leavitt discovered this relationship in 1912, working at the Harvard College Observatory for a salary that was frankly insulting even by the standards of the era, and her discovery became one of the most important tools in all of astronomy. Historians still argue whether she would have received the Nobel Prize had she lived longer, a question that says more about the biases of the early 20th century than about the quality of her work. Beyond the Cepheids, the ladder reaches to Type 1a supernovae, the thermonuclear explosions of white dwarf stars, which are so luminous they can be seen across billions of light years and whose peak brightness is remarkably uniform, making them excellent standard candles. By calibrating the brightness of nearby supernovae using Cepheids, and then observing distant supernovae, you can extend the measurement of the expansion rate deep into the cosmos. The team most prominently associated with this method is led by Adam Rees at Johns Hopkins University, who shared the 2011 Nobel Prize for the discovery of the accelerating expansion. Over the past decade, Rees and his colleagues in the SH0ES collaboration have relentlessly refined their distance ladder measurements, and their current best estimate of the Hubble constant sits at approximately 73 kilometers per second per megaparsec. They have beaten down their error bars to the point where the measurement is precise to about 1%. That is extraordinarily tight. There is very little room left for the number to wiggle. The other method comes from the cosmic microwave background, the relic radiation from the early universe. The European Space Agency's Planck satellite mapped this radiation with exquisite precision, measuring its temperature fluctuations across the entire sky. By analysing the statistical pattern of those fluctuations and feeding them into the lambda CDM model, cosmologists can extrapolate what the expansion rate should be today. The Planck-derived value is approximately 67.4 kilometers per second per megaparsec. Also very precise, also very confident. And there is the problem, 73 versus 67.4, a difference of about 8%. That might not sound catastrophic if you are comparing, say, the prices of two sandwiches, but in precision cosmology, where error bars have shrunk to slivers, an 8% gap is enormous. It is the difference between a universe that is roughly 12.8 billion years old and one that is 13.8 billion years old, which matters quite a lot when you are trying to explain galaxies that seem to have assembled themselves in an impossibly short window. The statistical significance of the discrepancy now exceeds 5 sigma, which in physics is generally the threshold for declaring a discovery. In other words, this is not a fluke. Something real is causing the mismatch. Before Webb, there was a persistent hope that the tension might be caused by some subtle, systematic error in the distance ladder. Maybe the Cepheid measurements were being contaminated by crowded stellar fields, where the light of neighbouring stars blended with the Cepheids and inflated their apparent brightness, leading to underestimated distances and overestimated expansion rates. This was a reasonable concern, and it was one of the key science goals Webb was designed to address. Its infrared vision and superior resolution would allow it to isolate Cepheids in crowded fields far more cleanly than Hubble ever could. So Webb looked. It observed Cepheids in several nearby galaxies that serve as critical rungs on the distance ladder. It resolved them with a clarity that made Hubble's images look like watercolour paintings viewed through a fogged window, and the result was definitive and deflating for anyone hoping the tension would simply evaporate. Webb confirmed the distance ladder measurements. The Cepheid photometry was not significantly biased by crowding. The SH0ES value held firm. If anything, the new Webb data tightened the error bars further, narrowing the already slim corridor in which the tension could be dismissed as a measurement artifact. There is a quirky footnote to this story that reveals something about the sociology of science. When the Webb Cepheid results were announced, some researchers who had staked their reputations on the tension being a systematic error went conspicuously quiet on social media, while others pivoted to proposing new exotic physics with an agility that would impress a gymnast. Science is a human enterprise, and human enterprises involve egos, and egos do not always handle being wrong with grace. But the data does not care about egos. The data simply is what it is, and what it is, increasingly, is uncomfortable. So now you have two layers of discomfort stacking on top of each other, impossible early galaxies, an expansion rate that refuses to agree with itself, and Webb, serene and golden at its Lagrange point, was already pivoting its mirrors toward a third unsettling thread, one woven from the very fabric of the dark energy that supposedly drives the cosmos apart. Dark energy, as you will recall from a few minutes ago when your eyes were perhaps slightly more open, is the name given to whatever is causing the expansion of the universe to accelerate. It accounts for roughly 68% of everything that exists, which is a staggering amount of cosmic real estate to assign to something that remains fundamentally mysterious. In the standard lambda-CDM model, dark energy is treated as the cosmological constant, a fixed energy density woven into the fabric of space itself. It does not change with time. It does not vary from place to place. It simply is a steady, relentless push that causes every cubic meter of space to nudge apart from every other cubic meter at an ever-increasing rate. This constancy is actually one of the model's most appealing features, because constants are simple, and simple things are easier to work with, easier to test, and easier to trust. But what if dark energy is not constant? What if it changes over time? What if the thing pushing the universe apart is not a steady hum but a variable signal, something that was stronger in the past and is now weakening, or something that was weaker and is now growing? This possibility has haunted theoretical cosmology for decades, lurking in models with names like quintessence and phantom energy, models that allow dark energy to have a dynamic equation of state, rather than the fixed value of -1 assigned by the cosmological constant. These models are mathematically elegant and physically intriguing, but until recently there has been no compelling observational evidence to favour them over the simpler constant explanation. The data was consistent with lambda, and in science, when the simple explanation fits, you do not complicate things without reason. The reason arrived, with characteristic understatement, in the form of a joint analysis combining Webb observations with data from the Dark Energy Spectroscopic Instrument, known as DESI. DESI is a ground-based survey that has been mapping the three-dimensional positions of tens of millions of galaxies and quasars, using their distribution to trace the expansion history of the universe over the past 11 billion years. It does this by measuring baryon acoustic oscillations, a fantastically named phenomenon that amounts to a cosmic ruler. In the early universe, sound waves propagated through the hot plasma of protons, electrons and photons, creating regions of slightly higher and slightly lower density. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, those sound waves froze in place, leaving a characteristic imprint on the distribution of matter. That imprint, a preferred separation scale of about 500 million light-years in today's expanded universe, shows up in the statistical clustering of galaxies and can be used to measure cosmic distances and expansion rates with impressive precision. When the DESI team published their first-year results in early 2024, there was a subtle but provocative signal buried in the data. The expansion history of the universe, as traced by baryon acoustic oscillations across different epochs, did not perfectly match the prediction of a constant dark energy. Instead, the data showed a mild preference for a model in which dark energy's equation of state varies with time, specifically one where dark energy was behaving differently in the recent past compared to the more distant past. The statistical significance was not overwhelming, hovering around the 2 to 3 sigma level, which in physics means interesting but not yet conclusive. It was the kind of result that makes half the community lean forward in their chairs and the other half cross their arms and wait for more data. But then Webb added its voice to the conversation. By providing independent constraints on cosmic distances and the properties of the early universe, Webb's observations of distant supernovae and gravitationally lensed galaxies offered complementary data that could either bolster or weaken the DSI hint. The combination of the two datasets, along with existing data from the Planck satellite and ground-based surveys, nudged the evidence further toward the dynamic dark energy scenario. Not definitively, not with the kind of resounding statistical certainty that would trigger champagne in physics departments, but enough to make the possibility feel real in a way it had not before, like a shadow that had always been in the corner of your vision finally taking shape. The implications of weakening dark energy are profound and frankly a little vertigo-inducing, so hold on to your blanket. In the standard model with a cosmological constant, the fate of the universe is relatively straightforward. The expansion accelerates forever, galaxies drift apart, stars burn out, black holes evaporate, and the cosmos ends in a cold, dark, empty whisper called the heat death. It is bleak, but it is stable. The rules do not change. The acceleration continues at a steady clip into eternity. If dark energy is weakening, however, the acceleration could slow down. In some models, it could stop entirely and even reverse, leading to a scenario where the universe eventually stops expanding and begins to contract, heading toward a big crunch that mirrors the Big Bang in reverse. Other models allow dark energy to cross a critical threshold and become phantom energy, an even more exotic beast that would cause the expansion to accelerate so violently that it tears apart galaxies, stars, atoms, and eventually the fabric of space-time itself in a catastrophic finale called the Big Rip. There is a quirky historical irony here that is worth savouring. Einstein introduced the cosmological constant to prevent the universe from changing, to keep it static and eternal and philosophically comfortable. A century later, the biggest question in cosmology is whether his constant is actually constant, and the answer to that question determines whether the universe ends in ice, fire, or something far stranger. Historians of physics love this kind of narrative loop, and scholars still argue whether Einstein's instinct to include the term was a deep physical intuition dressed up as a mistake, or simply a lucky accident that happened to anticipate a real phenomenon for entirely wrong reasons. Either way, lambda is back, and it might be misbehaving. You should know that the scientific community is being appropriately cautious about all of this. 2 to 3 sigma hints have a well-documented history of evaporating with more data. Physicists even have a darkly humorous name for this phenomenon, the look elsewhere effect, which accounts for the fact that if you search enough data for anomalies, you will inevitably find some that are purely statistical noise. DZ is collecting more data. Webb is continuing its survey observations. Other experiments, including the Vera C. Rubin Observatory, which is expected to begin its 10-year sky survey soon, will provide additional independent checks. But the trajectory of the evidence is moving in a direction that makes the constant dark energy crowd increasingly uncomfortable, and the dynamic dark energy crowd increasingly animated. And you, nestled in your bed, while the universe potentially rearranges its own fate, can drift a bit deeper, knowing that even the emptiness of space may be more complicated than anyone dared to model. While cosmologists were grappling with dark energy that might not be constant, and galaxies that grew too fast, Webb was quietly stirring up another corner of the dark matter debate, and this one might be the strangest of all. It found galaxies that appear to have almost no dark matter whatsoever. Now that might sound like a minor curiosity, a cosmic oddity to file alongside rogue planets and magnetars and all the other weird things the universe produces when nobody's looking. But the absence of dark matter in a galaxy is not a quirky footnote. It is a conceptual grenade. The entire framework of galaxy formation depends on dark matter being present, being abundant, and being the gravitational architect that pulls ordinary matter into the dense concentrations that become galaxies. A galaxy without dark matter is like a building without a foundation, and the fact that it exists and is standing forces you to ask either how the foundation was removed or whether buildings can somehow stand without one. The objects in question are called ultra-diffuse galaxies, and they're exactly as strange as their name suggests. They are roughly the size of the Milky Way in diameter, but contain only a tiny fraction of its stars, making them ghostly, spread-out collections of dim light that are extraordinarily difficult to detect. Some of these objects were first identified by ground-based surveys and the Hubble Space Telescope, but Webb's infrared sensitivity and resolution allowed astronomers to study their internal dynamics and stellar populations with unprecedented clarity. And what they found in several of these galaxies was unsettling. The stars were moving at velocities consistent with the gravitational pull of the visible matter alone. There was no need to invoke a dark matter halo to explain the rotation curves. The dark matter, if it had ever been there at all, was missing. The poster child for this phenomenon is a galaxy called NGC 1052-DF2, which had already made headlines before Webb launched, thanks to observations by a team led by Peter Van Dokkum at Yale. Van Dokkum's group measured the velocities of globular clusters orbiting the galaxy and concluded that its total mass was almost entirely accounted for by its visible stars and gas, leaving no room for a significant dark matter component. The result was immediately controversial. Other researchers challenged the distance estimates, arguing that if the galaxy were closer than Van Dokkum's team calculated, its intrinsic luminosity would be lower and the need for dark matter would reappear. The debate ping-ponged back and forth in journals and at conferences with the kind of polite ferocity that only academics can sustain. Webb stepped into this argument with the delicacy of a referee carrying a very high-resolution camera. Its observations helped refine the distance to NGC 1052-DF2 and its companion galaxy NGC 1052-DF4, which also appeared dark matter deficient. The revised measurements largely supported the original claims. These galaxies genuinely seem to contain far less dark matter than the standard model predicts, and perhaps none at all. Which is, to borrow a technical term from the field, deeply weird. There's a beautiful historical parallel buried in this discovery. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the Coma cluster of galaxies and noticed that the galaxies within it were moving far too fast to be held together by the gravitational pull of their visible mass alone. He proposed that some form of unseen matter, which he called Dunkelmaterie, dark matter, must be providing the extra gravitational glue. His colleagues largely ignored him for decades, partly because the evidence was not yet overwhelming, and partly because Zwicky had a personality that could generously be described as combative. He allegedly called his colleagues spherical bastards, because they were bastards no matter which angle you looked at them from. Historians still argue about whether his abrasiveness delayed acceptance of his ideas, or whether the scientific community simply was not ready for such a radical concept. Either way, Zwicky was right, and dark matter became a cornerstone of modern cosmology. Now, nearly a century later, Webb is finding galaxies that seem to be saying the opposite of what Zwicky discovered. Not that there is hidden mass everywhere, but that in some places the hidden mass is conspicuously absent. The irony is almost poetic. The universe spent decades convincing us that dark matter exists, and now appears to be demonstrating that it does not always show up where theory demands it should. This creates a fascinating fork in the theoretical road. One path leads to explanations within the standard dark matter framework. Perhaps these ultra-diffuse galaxies formed inside normal dark matter halos, but then lost their dark matter through gravitational interactions with nearby massive galaxies, a process called tidal stripping. In this scenario, the dark matter was there once, but was pulled away by the gravitational tides of a close encounter, leaving behind a galaxy of stars drifting in a halo-less void. There is some circumstantial evidence for this. In NGC 1052-, DF2 and DF4 are both in the vicinity of a large elliptical galaxy, NGC 1052, which could plausibly have done the stripping. Computer simulations have shown that tidal interactions can indeed remove dark matter, preferentially from smaller galaxies under certain conditions, though reproducing the extreme dark matter deficiency observed in these specific galaxies remains a challenge. The other path leads somewhere far more radical. A small but vocal community of physicists has long advocated for an alternative to dark matter, called modified Newtonian dynamics, or MOND, originally proposed by Mordechai Milgrom in 1983. MOND suggests that dark matter does not exist at all, and that instead the laws of gravity change at very low accelerations, the kind of accelerations experienced at the outer edges of galaxies. In MOND's framework, the flat rotation curves of galaxies are not caused by invisible mass, but by gravity itself behaving differently when it gets sufficiently weak. MOND has had some notable successes, particularly in predicting the rotation curves of individual galaxies, but it has struggled to explain large-scale phenomena like the cosmic microwave background and the dynamics of galaxy clusters without adding additional components that start to resemble dark matter by another name. Here is where it gets particularly delicious for anyone still awake. The discovery of galaxies without dark matter is actually a problem for MOND, not a victory. If gravity is modified everywhere, then every galaxy should show the effects. You should not find galaxies that behave as if standard Newtonian gravity alone is sufficient, because in MOND, Newtonian gravity is never sufficient at these scales. The dark matter deficient galaxies are easier to explain if dark matter is a real substance that can be added or removed from a galaxy, rather than a modification of gravity that is always present. So paradoxically, galaxies that lack dark matter may be some of the strongest evidence that dark matter actually exists as a physical entity, which is the kind of logical twist that makes theoretical physics simultaneously infuriating and beautiful. You're sinking deeper now, and the universe is getting stranger with every paragraph, and somewhere out in that cold void, Webb is turning its golden gaze toward objects even more unsettling than ghost galaxies with missing foundations. The objects Webb found next are the kind that make you reconsider the phrase monster in the dark. Supermassive black holes. Not the modest stellar mass black holes formed when large stars collapse, which are impressive enough in their own right, but the true behemoths, the ones that sit at the centres of galaxies and contain the mass of millions or billions of suns, compressed into a region of space-time so warped that not even light can climb out. You already know these things exist. The Milky Way has one called Sagittarius A star, a relatively quiet specimen weighing in at about 4 million solar masses. The galaxy M87 has a far more dramatic one, tipping the scales at roughly 6.5 billion solar masses, and it was the first black hole ever directly imaged by the Event Horizon Telescope in 2019, appearing as a fuzzy orange donut that graced the front pages of every newspaper on Earth and approximately half the coffee mugs sold in the following year, supermassive black holes are strange enough when you find them in the modern universe, where they have had 13.8 billion years to grow. The standard picture of their formation goes something like this. A massive star in the early universe collapses into a stellar mass black hole, perhaps 100 times the mass of the Sun. That seed black hole then grows by accreting surrounding gas, swallowing it in a swirling disk of superheated material that radiates fiercely as it spirals inward. Over billions of years, through steady accretion and occasional mergers with other black holes, the seed grows into the supermassive giants you see today. It is a slow, methodical process, governed by a speed limit called the Eddington limit, which sets the maximum rate at which a black hole can swallow matter. Beyond that rate, the radiation produced by the infalling material generates so much outward pressure that it actually pushes new material away, choking off the food supply. The Eddington limit is not absolute, and there are theoretical ways to exceed it briefly, but sustained super-Eddington accretion is difficult to maintain and even more difficult to model convincingly. Now here is what Webb found that scared people. It detected supermassive black holes in the very early universe at redshifts corresponding to a time when the cosmos was only about 600 to 800 million years old. And these were not modest seeds in the early stages of growth. They were fully fledged monsters, containing masses of hundreds of millions to over 1 billion solar masses. The timeline simply does not work. If you start with the stellar mass seed of 100 solar masses at the moment the first stars formed, roughly 200 million years after the Big Bang, and allow it to accrete at the maximum Eddington rate continuously without interruption for the next 400 to 600 million years, you end up with a black hole that is large but still falls dramatically short of 1 billion solar masses. The math has been checked repeatedly. The models have been run with generous assumptions, and the gap between what conventional accretion can produce and what Webb actually observed remains stubbornly wide. One of the most striking discoveries came from Webb's observation of a quasar called UHZ1, detected behind a galaxy cluster that was gravitationally lensing its light. Spectroscopic analysis placed this quasar at a redshift of about 10.1, meaning the light was emitted when the universe was only approximately 470 million years old. The black hole powering this quasar was estimated to be between 10 million and 100 million solar masses. While that is not the most massive early black hole Webb has found, the combination of its mass and its extreme distance created an acute problem for formation models. There is a quirky detail in the X-ray data obtained by the Chandra Space Telescope that makes this object even more interesting. The X-ray luminosity of UHZ1 was comparable to its infrared luminosity, a ratio that some theorists interpret as evidence that the black hole's mass is a significant fraction of the total mass of its host galaxy. In the modern universe, supermassive black holes typically represent less than 1% of their host galaxy's mass. In UHZ1, the ratio appeared to be far higher, suggesting that the black hole grew before or alongside the galaxy rather than after it, which inverts the standard picture of galaxy black hole coevolution in a way that is frankly disorienting. Even more dramatic was the discovery of a source designated GN-Z11, a compact galaxy at redshift 10.6, whose spectrum revealed signatures consistent with an active supermassive black hole accreting at a prodigious rate. GN-Z11 had been known before Webb, detected by Hubble as one of the most distant galaxies ever observed, but Webb's spectroscopy revealed features including highly ionized nitrogen lines that strongly suggested a powerful central engine was at work. The estimated black hole mass was in the range of 1 to 100 million solar masses, and the accretion appeared to be near or above the Eddington limit. Scholars still argue about the precise mass estimate because deriving black hole masses from spectral features at such extreme distances involves a chain of assumptions, each link carrying its own uncertainty. But even the most conservative interpretation leaves you with a black hole that is far too large for its cosmic age under conventional growth scenarios. The historical parallel here is worth noting. When quasars were first discovered in the early 1960s, they baffled astronomers completely. These point-like sources were extraordinarily luminous, and their spectra showed redshifts that placed them at enormous distances. Martin Schmidt's identification of the redshifted hydrogen lines in the quasar 3C273 in 1963 opened the door to understanding that quasars were powered by accretion onto supermassive black holes, but for years the idea was met with skepticism. How could so much energy come from so small a region? The answer turned out to be gravity, the most efficient energy source in the universe. A black hole converting in falling matter into radiation via an accretion disk can be up to 40 times more efficient than nuclear fusion. But efficiency does not solve the timing problem. You can be the most efficient eater in the world and still not be able to consume an entire buffet in 5 minutes. And so cosmology finds itself staring at a buffet that has been consumed in 5 minutes, with no satisfying explanation for how it happened. The conventional accretion model is too slow. Mergers between smaller black holes can help, but the merger rate required to build billion solar mass monsters in under 1 billion years is implausibly high. Something else must have been going on in the early universe, some mechanism for producing enormous black hole seeds that did not require starting from 100 solar mass remnant and slowly eating its way up. And this is where the theoretical landscape gets genuinely eerie, because the leading proposal involves a process that skips the star stage entirely and collapses primordial gas directly into a black hole, a mechanism that, if common, means the universe's most destructive objects may form far more easily than anyone previously imagined. The idea is called direct collapse, and it sounds almost too simple to be frightening. But once you sit with it for a moment, the implications settle over you like a cold draft from an open window. In the standard story of black hole formation, you need a star first. A massive star forms, burns through its nuclear fuel in a few million years, and then collapses under its own gravity when the outward pressure of fusion can no longer support its weight. The core implodes, the outer layers may be ejected in a supernova, and what remains is a stellar mass black hole, typically between 5 and perhaps 100 solar masses. This is a well-understood process. Messy in the details but conceptually clean. Star forms, star dies, black hole remains. The black hole then grows slowly by accreting surrounding gas, limited by the Eddington rate, over billions of years. Direct collapse skips the star entirely. In this scenario, a massive cloud of primordial gas, perhaps 100,000 to 1 million solar masses worth of hydrogen and helium, collapses directly into a black hole without ever igniting nuclear fusion. No star, no supernova, no intermediate stage, just gas becoming a black hole in what amounts to a single gravitational gulp. The resulting object is called a direct collapse black hole seed, and its initial mass could be anywhere from 10,000 to 1 million solar masses, orders of magnitude heavier than any stellar remnant. With a head start like that, reaching 1 billion solar masses within a few 100 million years becomes far more plausible. The Eddington limit is still a constraint, but you're starting the race so much closer to the finish line that the math begins to work. The conditions required for direct collapse are specific but not impossible. The gas cloud must be massive and must collapse rapidly enough that it does not fragment into smaller clumps that would form individual stars. Fragmentation is the enemy of direct collapse, and it's usually triggered by cooling. When gas cools, it loses thermal pressure and breaks apart into dense knots, each of which can ignite fusion and become a star. In the modern universe, gas cools efficiently because it contains heavy elements, metals in astronomer jargon, things like carbon and oxygen and iron that are exceptionally good at radiating away thermal energy. But in the very early universe, the first gas clouds were pristine, composed almost entirely of hydrogen and helium with no metals at all, because metals are forged inside stars and the first stars had not yet finished their work. Pristine gas cools much less efficiently, which means under the right conditions it can remain hot enough to resist fragmentation and collapse monolithically into a single enormous object. There is one additional ingredient that the models require, and it adds another layer of cosmic specificity that makes the whole scenario feel almost orchestrated. The gas cloud needs to be bathed in a strong flux of ultraviolet radiation from nearby star-forming regions. This radiation dissociates molecular hydrogen, the primary coolant available to pristine gas, effectively disabling the cloud's ability to cool and fragment. Without molecular hydrogen to radiate away energy, the gas stays hot, stays smooth, and falls inward as a single coherent mass. The requirement for a nearby ultraviolet source means that direct collapse does not happen in isolation. It happens in the neighbourhood of other early structures, close enough to be irradiated but not so close that the gas is disrupted entirely. It is a Goldilocks scenario, and as with most Goldilocks scenarios in astrophysics, the question is how often the conditions are actually met. This is where Webb's observations become crucial. If direct collapse black holes are common, you would expect to find numerous overmassive black holes in the early universe, which is precisely what Webb appears to be seeing. You would also expect to find galaxies where the central black hole constitutes an unusually large fraction of the total mass, because the black hole got its head start before the galaxy fully assembled around it. Again, this matches observations like UHZ-1 that you encountered just a few minutes ago, where the black hole mass was a strikingly large fraction of the host galaxy mass. And you would expect these objects to appear in environments with nearby sources of ultraviolet radiation, which is consistent with the clustered, actively star-forming regions where Webb's early black holes tend to be found. There is a quirky and somewhat haunting thought experiment that some astrophysicists have entertained in the wake of these discoveries. If direct collapse is a relatively common process in the early universe, then the cosmos may have produced enormous black holes before it produced enormous galaxies. The black holes came first, the galaxies built up around them later, and the supermassive monsters you see today at the centres of galaxies are not products of their host galaxies, but rather the original nuclei around which those galaxies crystallized. This inverts the traditional chicken-and-egg relationship between galaxies and their central black holes, and historians of science have pointed out that the question of which came first, the galaxy or the black hole, has been debated since the discovery of quasars in the 1960s. Scholars still argue about the answer, and Webb has not settled the debate so much as dramatically raised the stakes. The frightening part, if you're still registering fright at this hour, is not the existence of direct collapse black holes per se. It is what their existence implies about the universe's capacity for creating extreme objects with startling ease. In the standard picture, supermassive black holes are rare, precious endpoints of a long evolutionary process. They require specific conditions, long timescales, and a series of fortunate events to reach their final masses. In the direct collapse picture, the universe can mint them relatively quickly under conditions that may have been widespread in the early cosmos. The Dark Ages were not just dark because there were no stars yet. They may have been dark because some of the first massive objects to form were not luminous stars at all, but lightless gravitational traps, seeds of destruction sown into the fabric of space-time while the rest of the universe was still figuring out how to make starlight. And there is a particular particularly unsettling footnote that theorists have been chewing on quietly. If the conditions for direct collapse existed in the early universe, could analogous conditions exist today in exotic environments? Dense gas clouds in the centres of galaxy mergers, for instance, or in the turbulent environments around the most active galactic nuclei. The consensus is that modern conditions make direct collapse extremely unlikely, because the universe is now enriched with metals that enable efficient cooling and fragmentation. But unlikely is not impossible, and in a universe that has already surprised us this thoroughly, unlikely feels less reassuring than it used to. You might feel the weight of all this settling over you now, the strange heaviness of learning that the universe builds its most destructive objects more easily than expected. But Webb was not finished unsettling the scientific community. Even as it peered at ancient black holes and impossible galaxies, it was simultaneously turning its infrared gaze towards something much closer, much smaller, and in some ways much more personal. It was looking at the atmospheres of alien worlds, places where rain might fall and winds might blow, and what it found there was a complicated mixture of wonder and disappointment that strikes at the heart of humanity's oldest question. You have spent the last several minutes drifting through the deep past, visiting galaxies and black holes that existed billions of years before your planet even formed. Now Webb is going to bring you somewhere closer, not in time, but in emotional proximity. Because when a telescope looks at the atmosphere of another world and tells you what chemicals are floating in its sky, the question stops being abstract. It stops being about redshifts and mass functions and cosmological parameters. It becomes personal. Is anyone else out there? Is there anywhere else that rain smells like rain? That clouds part to reveal something resembling a sunset, that the air is breathable by something, anything, even something you would not recognize as alive. The technique Webb uses to read the atmospheres of exoplanets is called transmission spectroscopy, and it is one of the most elegant methods in all of observational astronomy. The principle is straightforward enough that you can picture it while half asleep. An exoplanet orbits its host star. Periodically, from our perspective, the planet passes in front of the star, an event called a transit. During the transit, a tiny fraction of the starlight passes through the thin shell of atmosphere surrounding the planet before reaching Webb's instruments. Different molecules in that atmosphere absorb light at different wavelengths, leaving characteristic fingerprints in the spectrum. By comparing the star's spectrum during a transit to its spectrum when the planet is not in the way, you can identify which molecules are present in the planet's atmosphere. It is like holding a piece of coloured glass up to a flashlight and figuring out what the glass is made of by seeing which colours get blocked. Hubble had performed crude versions of this analysis for a handful of exoplanets, mostly hot Jupiters, the bloated gas giants that orbit perilously close to their stars and have puffy, extended atmospheres that are relatively easy to probe. But Hubble's instruments lack the sensitivity and wavelength coverage to push into the infrared, where many of the most interesting molecular signatures live. Webb changed this overnight. Its instruments, particularly a NearSpec and MIRI, cover a broad swath of the infrared spectrum with a sensitivity that allows it to detect atmospheric features on smaller, cooler, and more scientifically tantalizing planets. One of Webb's first major exoplanet results came from the gas giant blue ASP39b, a hot Saturn-sized planet orbiting a Sun-like star about 700 light-years from Earth. Webb's transmission spectrum of WASP39b was a revelation. It detected water vapour, carbon dioxide, carbon monoxide, sodium, potassium, and most strikingly sulfur dioxide. That last molecule was particularly exciting because its presence implies active photochemistry in the planet's atmosphere, chemical reactions driven by starlight that produce new compounds. On Earth, photochemistry is responsible for the ozone layer, among other things, and finding it on another world meant that Webb could detect not just static inventories of chemicals, but dynamic atmospheric processes, weather in the broadest sense. The carbon dioxide detection alone was historic. It marked the first unambiguous identification of carbon dioxide in the atmosphere of a planet outside our solar system. Carbon dioxide is a greenhouse gas, a climate regulator, and a molecule intimately connected to both the geology and biology of Earth. Finding it on WASP 39b did not mean the planet was habitable. Far from it. The surface temperature is roughly 1100 Kelvin, which is hot enough to melt gold. But it demonstrated that Webb's instruments could pick up the very molecules that astrobiologists care most about. If carbon dioxide and sulfur dioxide could be detected on a roasting gas giant 700 light-years away, then detecting them on smaller, cooler, rocky worlds was within reach. The door was open, and Webb walked through it. Over the following months, the telescope trained its instruments on a growing catalogue of smaller exoplanets, probing the atmospheres of sub-Neptunes and super-Earths, worlds that have no analogue in our own solar system, but that appear to be among the most common types of planets in the galaxy. A quirky statistical fact that still astonishes planetary scientists is that the most common type of planet in the Milky Way is one that does not exist around our own Sun. Planets between the size of Earth and Neptune, sometimes called mini-Neptunes or super-Earths, depending on their density and composition, are everywhere, orbiting roughly 1 in 3 Sun-like stars. Understanding what these planets are made of and whether any of them could support life has become one of the driving questions of modern astronomy. One target that drew particular attention was GJ1214b, a warm sub-Neptune orbiting a nearby red dwarf star. Previous observations by Hubble had returned frustratingly flat spectra, suggesting that the planet's atmosphere was shrouded in high-altitude clouds or hazes that blocked the spectral fingerprints of the gases below. Webb's longer infrared wavelengths were expected to penetrate these clouds, and they partially delivered. The data hinted at a water-rich atmosphere, possibly a steam world with no solid surface, a planet that might be essentially one giant ocean of supercritical water beneath a thick, hazy sky. The results were preliminary and contested, with some teams favouring a hydrogen-dominated atmosphere with trace water, and others arguing for a more exotic composition. Scholars still argue about the true nature of GJ1214b, and the debate exemplifies the broader challenge of interpreting exoplanet spectra, where the data is real, but the number of possible atmospheric compositions that can fit the same observations is discouragingly large. Webb also observed the rocky exoplanet LHS 475b, an Earth-sized world orbiting a red dwarf star about 41 light-years away. The transmission spectrum was tantalizing in its flatness. It ruled out a thick hydrogen-dominated atmosphere but could not distinguish between a thin carbon dioxide-rich atmosphere, a tenuous atmosphere of some other composition, or no atmosphere at all. The ambiguity was maddening. Here was a rocky planet roughly the same size as Earth, orbiting in the habitable zone of its star where temperatures might permit liquid water, and Webb could tell you what it was not, but struggled to tell you what it was. It was like opening a letter from a stranger who might be saying something beautiful, but the ink was too faded to read. This frustration would deepen considerably when Webb turned its instruments toward one of the most anticipated targets in all of exoplanet science, a system of 7 rocky worlds orbiting a small, cool red dwarf star about 40 light-years away, a system that had captivated the public imagination and the astronomical community alike since its discovery was announced with great fanfare back in 2017. You already know its name. You have heard it whispered at the edges of popular science articles and breathless press releases for years. TRAPPIST-1. Even the name sounds like something from a fairy tale, though it actually derives from the deeply unsexy acronym for the transiting planets and Planetesimal Small Telescope, a Belgian robotic telescope that first detected the system. TRAPPIST. One is a red dwarf star, small and cool and dim, with a mass about 9% that of the Sun, and a luminosity roughly 2,000 times fainter. If you replace the Sun with TRAPPIST-1, the Earth would freeze solid almost instantly. But the 7 planets orbiting this little star are packed in so tightly that even its feeble warmth is enough to place several of them in or near the habitable zone, the orbital sweet spot where temperatures might allow liquid water to pool on a rocky surface. 3 of the planets, designated TRAPPIST-1e, F and G, sit squarely in this zone, and when the system was announced, the excitement was electric. Here were multiple roughly Earth-sized worlds in the habitable zone around a nearby star, all transiting regularly and therefore perfectly positioned for atmospheric characterization by the next generation of telescopes. The next generation of telescopes, of course, meant Webb. The hype was immense. News outlets ran headlines about potential alien oceans. Artists rendered lush, watery landscapes beneath ruddy skies. NASA held a press conference that had the energy of a movie trailer premiere. The public was primed for revelation, and scientists, while more cautious in their language, were privately giddy. TRAPPIST-1 represented the best opportunity humanity had ever had to characterize the atmosphere of a potentially habitable rocky world. If any of those planets held a thick Earth-like atmosphere rich in nitrogen and carbon dioxide and water vapor, Webb would see it. The spectral fingerprints would be there, written in the infrared, waiting to be read. The observations began, and the results began to arrive, and the mood began to shift. TRAPPIST-1b, the innermost planet, was the first to be studied in detail. It orbits so close to its star that it completes a year in just 1.5 Earth days, and its dayside temperature was expected to be high, but not impossibly so, perhaps comparable to Mercury. Webb measured the thermal emission from TRAPPIST-1b during a secondary eclipse, the moment when the planet passes behind the star and its own heat can be isolated by subtraction. The temperature it measured was consistent with a bare, airless rock. No atmosphere, no redistribution of heat from the day side to the night side, which would have been the telltale sign of winds carrying warmth around the planet. Just a scorched, naked surface, baking in the glow of its red dwarf host. This was not entirely unexpected. TRAPPIST-1b is too close to the star to be habitable, and red dwarf stars are notorious for their violent flare activity, eruptions of radiation, and charged particles that can strip atmospheres from close-in planets over millions of years. But it was still a blow to the narrative. The first TRAPPIST-1 world to be characterized had nothing to show. Then came TRAPPIST-1c, the second planet slightly farther from the star and receiving roughly the same amount of energy as Venus does from the Sun. Venus, despite being a hellscape of sulfuric acid clouds and crushing atmospheric pressure, at least has a thick atmosphere. TRAPPIST-1c was hoped to have something similar, some kind of dense carbon dioxide envelope that, while not hospitable, would at least demonstrate that rocky planets around red dwarfs can hold on to their air. Webb measured its thermal emission, and again the news was discouraging. The data was most consistent with either a bare rock or a very thin atmosphere at best. There was no evidence of a thick, Venus-like carbon dioxide atmosphere. Another world stripped bare. Another data point suggesting that the TRAPPIST-1 system might be harsher than the optimists had hoped. There is a historical parallel worth mentioning here that adds a layer of melancholy to the story. In the early 20th century, astronomers were convinced that Mars had canals, engineered waterways built by an intelligent civilization struggling to survive on a drying world. The astronomer Percival Lowell spent years mapping these canals, publishing detailed charts and impassioned books arguing for Martian life. when better telescopes and eventually spacecraft revealed Mars to be a cold, barren desert with no canals and no civilization, the disappointment was palpable. TRAPPIST-1 is not a perfect analogy, because no one was claiming to see canals, but the emotional arc is similar. A tantalizing possibility, amplified by hope and public attention, gradually deflated by the indifferent clarity of better data. Scholars still argue about whether the early TRAPPIST-1 results constitute a genuine crisis for habitability models, or merely a selection effect. The innermost planets are the easiest to characterize because they transit most frequently, but they are also the most exposed to stellar radiation and the least likely to retain atmospheres. The real prizes are TRAPPIST-1e, F and G, the habitable zone planets, and Webb observations of those worlds are ongoing but fiendishly difficult. The signals are smaller, the transits less frequent, and the atmospheric features, if they exist, are buried in noise that requires dozens of observations stacked together to tease out. It is painstaking work, the astronomical equivalent of listening for a whisper in a hurricane, and definitive results may take years. But the early returns have injected a note of caution into a field that had been running on optimism. The default assumption for years had been that rocky planets in habitable zones probably have atmospheres, because Earth does, and Earth is our only reference point. Webb is challenging that assumption, not by definitively proving that all rocky planets around red dwarfs are airless, but by showing that at least some of them are, and that the universe is under no obligation to make habitability easy or common. A quirky detail that emerged from the TRAPPIST-1 observations involves the star itself. Red dwarfs like TRAPPIST-1 are far more magnetically active than the Sun, and their flares can be hundreds of times more energetic relative to their luminosity. Webb caught several flares during its observations, spikes of ultraviolet and X-ray radiation that briefly overwhelmed the planetary signals and had to be carefully modelled and removed from the data. Each flare is a reminder that these planets live in a radiation environment that makes Earth's neighbourhood seem positively serene. Whether any atmosphere can survive such bombardment over billions of years is one of the most important open questions in exoplanet science, and the answer may determine whether red dwarf systems, which account for roughly 75% of all stars in the galaxy, are viable homes for life or cosmic dead ends dressed in habitable zone clothing. You might feel a faint pang of disappointment settling into your chest, and that is understandable. But the TRAPPIST-1 story is not finished, and even as some doors appear to be closing, Webb was simultaneously prying open another that led to one of the most explosive debates in modern astrobiology, centered on a puffy sub-Neptune world with a name that sounds like a license plate. The planet is called K218b, and it has been causing arguments in the astrobiology community since well before Webb pointed its mirrors at it. K218b orbits a red dwarf star about 120 light-years from Earth, placing it in the cosmic neighbourhood if not exactly next door. It is roughly 8.5 times the mass of Earth and about 2.5 times Earth's radius, making it a sub-Neptune, one of those common in-between worlds that could be anything from a miniature gas giant with a thick hydrogen envelope to something far more exotic. What made K218 be a compelling target was its temperature. It orbits within its star's habitable zone, receiving roughly the same amount of stellar energy as Earth receives from the Sun. For a sub-Neptune, that is an unusual combination, and it opened the door to a tantalizing possibility. What if K218b is not a mini-Neptune at all, but a Haitian world, a hypothetical class of planet with a hydrogen-rich atmosphere sitting atop a global liquid water ocean? The Haitian concept was proposed in 2021 by a team led by Niku Madhusudhan at the University of Cambridge. The idea is elegant in its simplicity. A planet too massive and too puffy to be truly Earth-like could still harbour surface conditions compatible with liquid water if its thick hydrogen atmosphere provides sufficient pressure and insulation. Hydrogen is a light, fluffy gas, so even a substantial hydrogen envelope would not crush the surface the way a dense carbon dioxide or nitrogen atmosphere might. In Madhusudan's models, a Hycean world could maintain temperate surface conditions across a wide range of orbital distances, making them potentially habitable in a way that traditional models had not considered. It was a speculative idea, clearly labelled as such, but it was testable, and Webb was the instrument that could test it. Webb observed K218b in early 2023, and the results, published later that year, landed on the astrobiology community like a flare in a dark room. The transmission spectrum showed clear detections of methane and carbon dioxide in the planet's atmosphere, along with a notable absence of ammonia. This chemical cocktail was significant. On a gas-dominated world with no surface, you would expect ammonia to be present alongside methane, produced by chemical equilibrium in the deep atmosphere. Its absence could indicate that something is removing it, and one possibility is a liquid water ocean at the base of the atmosphere, where ammonia would dissolve readily. The methane and carbon dioxide without ammonia was exactly the atmospheric fingerprint that Madhusudan's Hycean models predicted for a world with a surface ocean beneath a hydrogen sky. But the real bombshell was a tentative detection of dimethyl sulfide, abbreviated DMS. Tentative is doing heavy lifting in that sentence, and you should hold it firmly in your mind as you absorb what follows. Dimethyl sulfide is a molecule that on Earth is produced almost exclusively by living organisms, specifically by marine phytoplankton. It is the compound partly responsible for the smell of the sea, that briny, faintly sulphurous tang you associate with coastal walks and fish markets. It has no known significant abiotic source on Earth. If DMS were confirmed in the atmosphere of K218b, it would be the first potential detection of a biosignature, a chemical sign of life on a planet outside our solar system. The reaction was immediate, polarised and loud. Headlines around the world screamed about signs of life on an alien world. Social media erupted. Madhusudan's team was careful to emphasise the tentative nature of the detection, noting that the signal was at the edge of statistical significance and that additional observations were needed to confirm it. But nuance does not travel well on the internet, and within hours the story had been compressed into a binary. Either Webb found life or it did not. The messy, uncertain, beautifully complicated middle ground where science actually operates was largely lost in the noise. The skeptics mobilised quickly and with good reason. Several independent analyses questioned the robustness of the DMS detection, arguing that the spectral feature attributed to dimethyl sulfide could be explained by other molecules or by systematic noise in the data. There is a quirky technical challenge here that illustrates why exoplanet atmospheric science is so fiendishly difficult. Many molecules have overlapping spectral features in the infrared. DMS absorbs light at wavelengths that are close to features produced by methane and other hydrocarbons. Disentangling these overlapping signatures requires precise modelling of the entire atmospheric spectrum, and the models are only as good as the assumptions that go into them. Assumptions about temperature structure, cloud properties, atmospheric mixing, and chemical abundances. Change one assumption, and the DMS feature can appear or disappear like a mirage. Other critics targeted the Hycean interpretation itself. Some atmospheric modelers argued that K218b's observed spectrum could be equally well explained by a mini-Neptune with no surface at all, just a deep hydrogen-helium atmosphere with trace methane and carbon dioxide produced by ordinary chemistry at high temperatures and pressures. In this scenario, there is no ocean, no surface, no place for life to gain a foothold, and the absence of ammonia has alternative explanations involving photochemistry or atmospheric dynamics. Historians of science have noted that the debate over K2-18b mirrors earlier controversies such as the claim of fossilized Martian bacteria in the meteorite ALH 84001, announced with great fanfare by NASA in 1996 and subsequently challenged by multiple lines of evidence. Scholars still argue whether ALH 84001 contains genuine biosignatures or whether the features were produced by non-biological processes, and 2 decades later the question remains unresolved. K2-18b may follow a similar trajectory, hovering in an ambiguous zone where the data is suggestive but not definitive, feeding hope and skepticism in equal measure. Madhusudhan's team has requested additional Webb observing time to strengthen or refute the DMS detection, and those observations are expected to provide significantly more data at the critical wavelengths. If DMS is confirmed with higher confidence, it will not be proof of life. It will be evidence consistent with life, which is a very different statement, one that scientists understand intuitively, but that the public and the media often struggle with. Proof of life would require either direct imaging of biological structures, detection of multiple independent biosignatures that cannot be explained by any known abiotic process, or, ideally, both. A single molecule on a single planet with a single set of observations is a clue, not a verdict. But even as a clue, it is extraordinary. And as you lie there, perhaps imagining phytoplankton drifting in an alien ocean under a hydrogen sky lit by a dim red star, you can feel the question sharpening itself against the silence of the night. If life is there, why have we not heard from it? And if life is not there, if world after world turns out to be barren or ambiguous or stripped of the very air that complex chemistry requires, what does that silence mean? The silence has a name. It is called the Fermi paradox, and it has been gnawing at the edges of scientific thought since a summer afternoon in 1950, when the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory, and, in the middle of a conversation about flying saucers and the probability of interstellar travel, asked a question so simple and so devastating that it has haunted every generation of scientists since. Where is everybody? The logic behind the question is almost painfully straightforward. The Milky Way contains somewhere between 100 billion and 400 billion stars. A significant fraction of those stars have planets. A significant fraction of those planets are rocky and orbit within habitable zones. The galaxy is roughly 13 billion years old, which means that even if intelligent civilizations arise rarely, they have had an enormous amount of time to do so. A civilization with even modest interstellar travel capability, nothing exotic, just spacecraft traveling at a small fraction of the speed of light, could theoretically colonize the entire galaxy in a few tens of millions of years. That sounds like a long time, but compared to the age of the galaxy, it is a blink. So if intelligent life is even moderately common, the galaxy should be teeming with evidence of it. Signals, structures, probes, megaprojects, something. And yet, as far as we can tell, the galaxy is quiet. No signals, no structures, no visitors. Just an enormous, echoing emptiness that gets louder the more carefully you listen. Before Webb, the Fermi paradox could be softened by ignorance. We simply did not know enough about exoplanet atmospheres, about the frequency of habitable conditions, about the chemistry of alien worlds, to make any strong claims about the prevalence of life. The paradox was more of a thought experiment than an empirical constraint. You could wave your hands and say maybe habitable planets are rarer than we think, or maybe atmospheres are stripped away more often than we assumed, or maybe life requires some extraordinarily unlikely chemical accident, and the paradox would politely wait in the corner while you continued your research. Webb is eroding that comfortable ignorance. every observation it makes narrows the range of plausible answers. If TRAPPIST-1 planets turn out to be airless, that tells you something about the viability of red dwarf habitable zones, and since red dwarfs constitute roughly 3/4 of all stars, that one result has enormous statistical implications. If K218b's biosignature hint evaporates with more data, that pushes back the timeline for finding chemical evidence of life. If planet after planet reveals atmospheres dominated by carbon dioxide, with no trace of biogenic gases, the silence deepens, and if, conversely, biosignatures start appearing on multiple worlds, the paradox sharpens in the opposite direction, because then the question becomes not whether life exists, but why it never seems to develop into anything that reaches out and says hello. This is where the Great Filter hypothesis enters the conversation, and it is exactly as ominous as it sounds. The Great Filter is a proposed explanation for the Fermi paradox that suggests there is some extraordinarily difficult step in the evolution from simple chemistry to galaxy-spanning civilization, a bottleneck so severe that almost nothing gets through. The critical question is where the filter sits in the timeline. If it is behind us in our past, then it means the step from non-life to life, or from single-celled life to complex multicellular organisms, or from animals to intelligence is staggeringly rare. We got lucky. Most planets never make it. The silence is explained by the fact that the galaxy is full of sterile worlds, or worlds stuck at the microbial stage, and we are one of the extraordinary few who punch through. If the filter is ahead of us, in our future, the implication is considerably darker. It means that reaching our level of technological development is not particularly rare, but surviving much beyond it is. Civilizations arise, develop technology, and then destroy themselves or are destroyed by natural processes before they can spread across the stars. Nuclear war, climate collapse, artificial intelligence gone wrong, a pandemic, a gamma-ray burst sterilizing the home planet. The specific mechanism varies depending on who is telling the story, but the outcome is the same. The galaxy is quiet because civilizations keep dying before they can make themselves heard. There is a quirky sociological detail about the Great Filter that is worth noting. When astrobiologists discuss it in professional settings, they tend to be measured and analytical. When they discuss it informally over drinks at conferences, the tone shifts noticeably. The ahead-of-us version of the filter makes people genuinely uneasy. It is one thing to intellectually entertain the possibility that civilization has an expiration date. It is another thing to look at the evidence accumulating from a $10 billion telescope and realize that the evidence might be pointing in that direction. Historians of science have observed that the psychological impact of astronomical discoveries often lags behind the discoveries themselves. It took decades for the full implications of Copernicus displacing Earth from the center of the universe to sink into the cultural consciousness. The implications of the Fermi paradox sharpened by Webb may follow a similar slow arc. Webb's contribution to this conversation is not definitive, and it would be irresponsible to suggest otherwise. The telescope has observed a handful of exoplanet atmospheres out of a galaxy containing billions of planets. The sample size is minuscule, the observations are still in their early stages, and the interpretive challenges are immense. But the direction of travel is clear. Every atmosphere that turns out to be sterile, every habitable zone planet that proves to be stripped bare, every ambiguous biosignature that resists confirmation adds a tiny weight to the silence side of the scale. And every confirmed biosignature, if one ever arrives, would simultaneously be the most thrilling and the most terrifying discovery in human history, because it would mean life is easy, and the filter, whatever it is, must lie elsewhere. Scholars still argue about whether the Fermi paradox is even a genuine paradox, or merely a reflection of our limited search capabilities and anthropocentric assumptions. Perhaps civilizations exist but communicate in ways we cannot detect. Perhaps they're deliberately hiding, a scenario called the dark forest hypothesis, popularized by the Chinese science fiction author Liu Cixin, in which civilizations stay silent because announcing your presence in a universe of unknown intentions is an existential risk. Perhaps the universe is simply too vast and too old for the fleeting window of any single civilization's existence to overlap with our own. These are possibilities, not answers, and the distinction matters. What Webb offers is not resolution but clarity. It is sharpening the question, stripping away the comfortable maybes and replacing them with data. And data, even when it is inconclusive, has a way of making the universe feel more real and more consequential than any amount of speculation. You lie there in the dark, and the silence around you, the ordinary domestic silence of your room, takes on a faintly cosmic quality. Not threatening, just deep. Just very, very deep. Let the darkness soften for a moment, because Webb has not spent all its time delivering existential vertigo. Some of what it has seen is purely, breathtakingly beautiful, and even the beauty carries surprises that have rewritten what astronomers thought they knew about how stars are born. You're going to visit a stellar nursery now, and the word nursery should conjure warmth and softness and tiny new things, which is partly accurate and partly misleading, because stellar nurseries are among the most violent places in the universe, and the tiny new things in question are thermonuclear furnaces millions of times more massive than your entire planet. The image that first stunned the world was Webb's view of the Carina Nebula, specifically a region along its edge that the science team nicknamed the Cosmic Cliffs. You may have seen this image. It looks like a vast, craggy mountainscape rendered in amber and rust and deep teal, peaks and valleys of gas and dust illuminated by the fierce radiation of nearby hot young stars. The visual resemblance to a terrestrial landscape is uncanny, and it is entirely coincidental. There are no mountains in the Carina Nebula. What you are seeing is the boundary between a dense cloud of molecular gas and the cavity carved into that cloud by the ultraviolet radiation and stellar winds of massive stars. The process is called photoevaporation, and it is essentially the star eating away at its own birth cloud, sculpting dramatic ridges and pillars as denser knots of gas resist the onslaught, while thinner regions are blown away. Hubble had imaged the Carina Nebula before, beautifully, but Hubble saw it in visible light, which meant the dense interior of the cloud was opaque. You could see the surface, the glowing edges, the dramatic silhouettes, but the stars being born inside were hidden behind curtains of dust. Webb's infrared vision cut through those curtains like morning light through a bedroom blind. Suddenly, the interior of the nebula was visible, and what it revealed was a landscape teeming with newborn stars, protostars still embedded in their natal cocoons of gas, jets of material streaming outward at hundreds of kilometers per second, and intricate structures that no simulation had predicted in such abundance. The jets were particularly surprising. Young stars in the process of forming accrete material from a surrounding disk, and as they do, they launch narrow, high-speed jets of gas from their magnetic poles, a process that astronomers call bipolar outflow. These jets were known before Webb, but Webb revealed them in staggering numbers and detail. Hundreds of previously undetected jets appeared in the Carina image, many from protostars so deeply embedded that no other telescope could see them. Some jets extended for light years, carving tunnels through the surrounding gas like cosmic fire hoses. Others were short and stubby, suggesting very young protostars that had only just begun their outflow activity. The sheer density of jets indicated that star formation in this region was more active and more chaotic than the best models had predicted, a theme that was becoming increasingly familiar in Webb's young career. Then there were the pillars of creation, perhaps the most iconic astronomical image ever taken, originally captured by Hubble in 1995 and recaptured in higher resolution in 2014. The pillars are towering columns of gas and dust in the Eagle Nebula, roughly 6,500 light-years from Earth, sculpted by the same photoevaporation process at work in the Carina Nebula. They're dense enough to resist the radiation of nearby hot stars, and at their tips and along their surfaces new stars are being born under the compression of the very forces that are slowly destroying the pillars themselves. It is a profoundly poetic process. Creation and destruction intertwine so completely that separating them becomes meaningless. Webb's image of the pillars was released in October 2022, and it immediately became a cultural phenomenon, printed on posters, shared millions of times, tattooed on forearms. But beyond the aesthetic impact, the scientific content was revelatory. Webb's infrared view stripped away the nebular gas and revealed the stars within behind the pillars with a clarity that made Hubble's image look like an impressionist painting. Young stars glowed fiercely at the tips of the pillars. Background galaxies, entirely invisible in Hubble's image, dotted the space between the columns, and the structure of the dust itself was resolved into filaments and knots of extraordinary complexity, patterns that carry information about the magnetic fields, turbulence, and gravitational fragmentation processes that govern how stars condense out of interstellar gas. A quirky discovery that emerged from Webb's nebula observations involved objects called free-floating planetary mass objects, or FFPMOs, which is the kind of acronym that only astronomers could love. In the Orion Nebula, Webb identified dozens of objects with masses comparable to Jupiter that are not orbiting any star. They are drifting freely through the nebula, untethered, alone. Some of these objects appear to exist in pairs, binary systems of planet-mass objects orbiting each other in the void, which was deeply confusing because no established formation mechanism easily explains how two Jupiter-mass objects end up gravitationally bound to each other without a star involved. Some researchers propose that these were planets ejected from forming star systems that happened to find each other, a cosmic meet-cute of extraordinary improbability. Others suggested they formed like stars, by direct gravitational collapse of small gas clumps, which would blur the boundary between what counts as a planet and what counts as a failed star. Historians of astronomy have noted that the definition of planet has been contested since the International Astronomical Union demoted Pluto in 2006, and scholars still argue whether that decision was scientifically principled or politically motivated. Webb's free-floating objects add another layer to this definitional headache. What all of these observations share is a common message. Star formation is messier, more vigorous, and more varied than the clean, orderly process described in textbooks. Stars are not born gently. They are born in violence, in compression, in radiation, in magnetic chaos, and the details of that violence matter because they determine the properties of the stars that emerge and the planetary systems that form around them. Webb is showing that our models of star formation, while broadly correct, were smoothed and simplified in ways that missed significant features. The universe, as it turns out, does not read the textbooks, and its nurseries are wilder places than anyone had drawn on the blackboard. The wildness extended beyond the nurseries and into the chemistry itself, because when Webb turned its spectrographs toward the earliest galaxies, the ones causing all the cosmological commotion you heard about earlier, it found that the chemical composition of the young universe was not what anyone had ordered. The first generation of stars, the ones that lit up after the cosmic dark ages, were supposed to be chemically pristine. Born from gas that had never been processed through a stellar interior, they should have contained only hydrogen, helium, and the faintest trace of lithium, the three elements forged in the Big Bang itself. These hypothetical pristine stars are called population 3 stars, and they occupy a special place in astrophysics partly because of their theoretical importance, and partly because nobody has ever definitively observed one. Population 3 stars are expected to have been enormous, perhaps hundreds of times the mass of the Sun, burning fast and hot and dying young in spectacular supernovae that seeded the surrounding gas with the first heavy elements. Those heavy elements, everything from carbon and oxygen to iron and gold, would then be incorporated into the next generation of stars, population 2, which would in turn live, die, and enrich the gas further, eventually producing the chemically rich population 1 stars like the Sun, whose planetary systems contain enough heavy elements to build rocky worlds and organic molecules, and eventually creatures who lie in bed listening to podcasts about telescopes. This chemical enrichment story, called galactic chemical evolution, is one of the foundational narratives of astrophysics. It is elegant, sequential, and logical. First-generation stars make the first metals. Second-generation stars make more. Third-generation stars swim in a rich chemical soup. The timeline is long, the process is gradual, and by the time you reach a universe 1 billion years old, you expect to see modest but measurable levels of heavy elements in the gas and stars of early galaxies. What you do not expect to see is what Webb actually found. Webb's spectroscopic observations of galaxies at redshifts between 6 and 10 revealed chemical abundances that were shockingly high. Nitrogen, in particular, appeared at levels far exceeding what standard chemical evolution models predict for such young galaxies. Carbon and oxygen were also elevated. These are elements that require stellar processing to produce, and producing them in the quantities Webb observed requires either an enormous number of stars forming and dying very quickly, or a type of stellar population that enriches its surroundings far more efficiently than anything in the standard models. The nitrogen problem is especially acute. In conventional astrophysics, nitrogen is primarily produced through a process called the CNO cycle, which operates in the cores of stars more massive than about 1.5 solar masses. The CNO cycle converts hydrogen into helium using carbon, nitrogen, and oxygen as catalysts, and it produces nitrogen as a byproduct. But the CNO cycle requires pre-existing carbon and oxygen to function, which means you need at least one prior generation of stars to have produced those seed elements before the nitrogen factories can spin up. This creates a time delay. You cannot produce large quantities of nitrogen until you have already produced significant amounts of carbon and oxygen, and that takes time. More time than the young universe appears to have had. Several creative solutions have been proposed, each carrying its own flavour of cosmic strangeness. One possibility involves very massive stars, perhaps the elusive population 3 behemoths, that burn through the CNO cycle at accelerated rates and then explode, dispersing nitrogen-enriched material into their surroundings. If the first generation of stars was dominated by these massive objects, as some models suggest, the chemical enrichment could have been front-loaded, delivering heavy elements faster than a more typical stellar population would. Another possibility involves so-called Wolf-Rayet stars, extremely massive and luminous stars that shed their outer layers in powerful stellar winds, exposing the nucleosynthetic products of their cores directly to the interstellar medium. Wolf-Rayet stars are known to be prolific sources of nitrogen, and if they were more common in the early universe than in the present day, they could account for at least part of the excess. A more exotic explanation involves supermassive stars, objects with masses exceeding 1,000 solar masses that may have existed briefly in the very early universe under the same conditions that could produce direct collapse black holes. Remember those from a few sections back, the primordial gas clouds that collapse without fragmenting. If such clouds collapsed part way, igniting fusion before ultimately imploding, the resulting supermassive star could have processed enormous quantities of hydrogen through the CNO cycle during its short, brilliant life, flooding its surroundings with nitrogen before dying in an explosion that would make ordinary supernovae look like firecrackers. This idea is speculative and difficult to test directly, but it connects two of Webb's most surprising findings, the overmassive black holes and the overabundant nitrogen, into a single narrative about extreme conditions in the early universe. There is a quirky observational detail that adds texture to this chemical mystery. Several of Webb's high redshift galaxies show nitrogen to oxygen ratios that resemble the ratios found in the peculiar nitrogen-loud quasars of the nearby universe, a class of active galactic nuclei known for their strong nitrogen emission lines. Scholars still argue about what produces the extreme nitrogen enrichment in these local quasars, with proposals ranging from unusual star formation histories to chemical enrichment by the accretion disks around supermassive black holes themselves. The resemblance between the chemistry of the early universe and these modern oddballs is either a coincidence, a clue, or a cosmic joke, and nobody is entirely sure which. What is clear is that the chemical history of the universe is not the smooth, gradual escalator that textbooks describe. It is more like a series of rapid bursts punctuated by quiet intervals, with the earliest bursts being far more intense than anyone modelled. The universe did not politely accumulate its elements over billions of years. It front-loaded the heavy stuff, enriching its first galaxies with a speed and efficiency that suggests the early cosmos was a far more extreme environment than the relatively sedate universe you inhabit today. And this matters. It matters because chemistry determines what kinds of planets can form, what kinds of molecules can assemble, and ultimately what kinds of complexity are possible. If the early universe was already rich in carbon, nitrogen and oxygen within its first few 100 million years, then the building blocks of organic chemistry, the raw ingredients of life as you know it, were available far earlier than anyone assumed. The implications ripple forward through cosmic time, and they touch something you will visit soon. The question of where all of this is heading, not just scientifically, but existentially. So here you are, somewhere between waking and sleep, having travelled through impossible galaxies, monstrous black holes, barren exoplanets, tentative whispers of alien biology, and a universe that enriched itself with the ingredients of complexity far faster than any model predicted. It is time to pull the threads together and ask the question that has been lurking beneath every section, like a bass note you feel more than hear. Where is all of this going? Not just the science, not just the next Webb observing cycle, but the universe itself. What is the fate of everything? The answer, until fairly recently, seemed settled. Lambda CDM, with a cosmological constant pointed toward a future called the Big Freeze, sometimes more dramatically called the heat death of the universe. In this scenario, dark energy continues to push the expansion of the cosmos at an ever-increasing rate, and the consequences unfold over timescales so vast they make the current age of the universe look like the first tick of a clock. Galaxies in the local group, the gravitationally bound cluster that includes the Milky Way and Andromeda, will eventually merge into a single giant elliptical galaxy, sometimes whimsically called Milkomeda. But every galaxy beyond the local group will be carried away by the expansion until its light can no longer reach us. The observable universe will shrink, not because space is contracting, but because the expansion is carrying distant objects beyond the cosmic horizon faster than their light can bridge the gap. One by one, the stars in Milkomeda will exhaust their nuclear fuel. The last red dwarfs, the slow-burning embers of the stellar population, will flicker out in roughly 100 trillion years. After that, the universe enters a long, dark era of cooling remnants. White dwarfs crystallize and fade. Neutron stars cool to the temperature of the void. Black holes remain. slowly evaporating through Hawking radiation over timescales so incomprehensibly long that writing them in standard notation would require more zeros than this entire script contains. Eventually, in the deepest imaginable future, even the black holes are gone. The universe is a diffuse, cold, empty expanse of photons and subatomic particles drifting apart at an ever-increasing rate. Entropy has won. Structure has dissolved. The cosmos does not end with a bang or a whimper, but with a silence so complete that the word silence does not do it justice. This is the heat death, and for 2 decades it has been the consensus forecast for the future of everything. But remember that dark energy might not be constant. Remember the hints from DESI, bolstered by Webb, that dark energy's equation of state may be varying with time. If dark energy is weakening, the forecast changes dramatically. In one scenario, the weakening continues until dark energy effectively fades away. Without the accelerating push, the expansion of the universe slows. Gravity, patient and persistent, begins to reassert its dominance. Over billions of years, the expansion halts and reverses. The universe begins to contract slowly at first, and then with gathering momentum, galaxies approaching each other, the cosmic microwave background blue shifting and heating, the sky brightening as the observable universe compresses. Eventually, everything collapses back into a singular state of unimaginable density and temperature, a mirror image of the Big Bang. This is the Big Crunch, and it carries a strange, almost cyclical poetry. The universe that began in fire ends in fire, and some speculative models propose that the crunch could trigger another Big Bang, beginning the cycle anew. An oscillating universe, breathing in and out across epochs of time, each breath a complete cosmic history from creation to annihilation. In another scenario, dark energy does not weaken but strengthens, growing more intense over time. This is the phantom energy model, and its endpoint is the most violent fate imaginable. As the expansion accelerates beyond all bounds, the force tearing space apart begins to overpower the forces that hold structures together. First, galaxy clusters are ripped apart, their member galaxies flung into isolation. Then individual galaxies disintegrate, their stars scattered like seeds in a hurricane. Then stellar systems dissolve, planets torn from their orbits. Then the stars themselves are shredded, then planets, then molecules, then atoms. In the final instant, space-time itself is torn apart in a singularity of infinite expansion. This is the Big Rip, and it could happen in as little as 20 to 30 billion years from now, under certain parameter choices, which is far enough away to be abstractly terrifying rather than personally concerning, but close enough to feel viscerally uncomfortable when you think about it at 1 a.m. There is a historical footnote worth savouring here. The concept of the Big Rip was first formally described in a 2003 paper by Robert Caldwell and colleagues, and it emerged from a mathematical possibility that most cosmologists initially dismissed as unphysical. The phantom energy required for the Big Rip violates certain energy conditions in general relativity, conditions that physicists generally assume hold true because violating them leads to all sorts of theoretical pathologies, including the possibility of time travel and causality violations. Historians of physics note that energy conditions have been violated before in quantum field theory, most famously in the Casimir effect. So dismissing phantom energy purely on theoretical grounds is not as straightforward as it might seem. Scholars still argue about whether phantom energy is a genuine physical possibility or a mathematical artifact, and the debate has taken on new urgency now that observational data is at least mildly flirting with the idea. And then there is the possibility that has no established name, the scenario that emerges if the data continues to surprise, in ways that do not fit any existing model. Perhaps dark energy transitions from one behaviour to another. Perhaps it oscillates. Perhaps it couples to dark matter or to ordinary matter in ways that have no precedent in current theory. Perhaps the universe's future involves phases and transitions that we do not have the conceptual vocabulary to describe, the way a medieval scholar would lack the words to describe a superconductor or a quark-gluon plasma. This is the genuinely humbling possibility, the one that sits quietly beneath all the specific scenarios, reminding you that every forecast is only as good as the physics it is built on, and the physics, as Webb keeps demonstrating, may be incomplete. A quirky thought experiment that cosmologists occasionally indulge in goes like this. Imagine explaining the fate of the universe to someone from 500 years ago. You would need to first explain that the universe is expanding, then that the expansion is accelerating, then that the acceleration might be changing, then that the nature of the force driving it is unknown, and finally, that the ultimate fate of everything depends on the properties of that unknown force. At some point in this explanation, your medieval listener would probably conclude that you are describing theology, not physics, and honestly, at the bleeding edge of cosmology, the distinction can feel thinner than you might be comfortable admitting. There's a kind of fear that does not make your heart race or your palms sweat. It is quieter than that. It settles somewhere behind your sternum, not as panic but as weight, a slow, heavy recognition that the thing you are looking at is bigger than your ability to comprehend it, and that this incomprehension is not temporary. It is structural. It is built into the relationship between a human mind, which evolved to track fruit on branches and threats in tall grass, and a cosmos that operates on scales and timelines that have no analogue in the sensory world you are designed to navigate. This is the kind of fear that Webb's discoveries have stirred in the scientific community, and it is worth spending a moment with it, because it is not the fear of a specific threat. Nobody is worried that a direct collapse black hole is going to appear in the solar system, or that dark energy is going to rip apart your house next Tuesday. The fear is epistemic. It is the fear of not knowing, deepened by the realization that each new answer reveals the silhouette of a larger question hiding behind it. Webb was built to answer questions, and it has answered many of them with extraordinary precision and clarity. But the net effect of those answers has been to expand the territory of the unknown faster than the territory of the known, which is not a failure of the telescope but a feature of scientific exploration at the frontier. Consider what you have encountered tonight. The impossible early galaxies challenged the timeline of structure formation, suggesting that galaxies assembled faster or differently than the standard model predicts. The Hubble tension revealed a crack in the measurement of the universe's expansion, a crack that Webb confirmed is real and not a mirage. The hints of dynamic dark energy threaten to upend the most basic assumption about the force driving cosmic acceleration. The dark matter deficient galaxies complicated the story of what dark matter does and where it lives. The supermassive early black holes broke the growth models and demanded exotic formation channels like direct collapse. The exoplanet atmospheres offered tantalizing but ambiguous clues about habitability and life. The chemical enrichment of early galaxies arrived too fast and too heavy, and through it all, the Fermi paradox sharpened its question to a finer point, the silence of the universe growing more conspicuous with every new data release. Each of these findings individually is manageable. Scientists are exceptionally good at absorbing surprises, adjusting models, and moving forward. That is what science does. But taken together, the cumulative weight of Webb's surprises paints a picture of a universe that is stranger, more dynamic, and less well understood than the confident tone of pre-Webb cosmology suggested. The Lambda CDM model is not dead. It is still the best framework available, and no single observation has delivered a fatal blow. But it is bruised, and the bruises are accumulating in a pattern that suggests something deeper may need to change. Historians of science would recognize this moment. It resembles what Thomas Kuhn described as the accumulation of anomalies that precedes a paradigm shift, the slow build-up of observations that the reigning framework cannot comfortably accommodate. Kuhn argued that scientific revolutions do not happen when a theory is disproven by a single decisive experiment. They happen when the weight of anomalies becomes too great to ignore, and a new framework emerges that explains both the old data and the new. Scholars still argue about whether Kuhn's model of scientific revolutions is accurate, or whether science progresses more gradually and less dramatically than he suggested, but the parallel is difficult to dismiss entirely. Cosmology in the age of Webb feels like a field approaching a tipping point, though what lies on the other side of that point remains unclear. There is a peculiar emotional texture to this uncertainty that deserves attention, because scientists are human, and their responses to the unknown are shaped by the same psychological forces that shape yours. In interviews and panel discussions and late-night threads on academic social media, you can detect a range of reactions to Webb's findings that mirror the stages of processing any major disruption. Some researchers express exhilaration, the thrill of working at a moment when everything's in play and the textbooks might need rewriting. Others express frustration, particularly those whose careers have been built on models that now appear incomplete. A few express something closer to awe, a quiet acknowledgement that the universe is under no obligation to be comprehensible, and that encountering its strangeness directly is a privilege even when it is uncomfortable. A quirky example of this emotional complexity surfaced at a major astronomy conference in 2023, where a senior cosmologist, during a panel on Webb's early results, paused mid-sentence and said something to the effect of, "I have spent 30 years building models of galaxy formation, and this telescope is telling me I was wrong about the first chapter." The audience laughed, but the laughter had an edge to it, the kind of laughter that acknowledges a truth too large to process without deflection. That moment captures something essential about where the field stands. The data is real, the surprise is genuine, and the path forward requires willingness to sit with not knowing that runs counter to every instinct a scientist is trained to follow. And yet, paradoxically, this is precisely why Webb is one of the greatest scientific instruments ever built. Not because it confirmed what we expected, but because it did not. The value of a telescope is not measured in the number of predictions it validates, but in the number of genuine surprises it delivers, because surprises are where new understanding begins. Every crack in the standard model is an invitation. Every anomaly is a trailhead. Every moment of epistemic discomfort is the feeling of the frontier being pushed outward, making room for ideas that have not been thought yet, and theories that have not been formulated. You can feel this, even half asleep. The universe is not what you were told it was. It is more. It is stranger. It is less settled and more alive with possibility than any model can currently contain. And somewhere out there, 1,000,000 miles from your pillow, a golden telescope is still collecting photons from the edge of time, still adding data to the pile, still quietly expanding the territory of what humanity does not yet understand. The fear is real, but so is the wonder, and tonight in the soft darkness of your room, they are the same thing. That golden telescope drifts in its slow orbit around the second Lagrange point, and if you could somehow float beside it, which you cannot because the vacuum would be immediately and comprehensively fatal, but let us pretend, you would see something remarkable in its stillness. Webb does not look like a machine in a hurry. It does not whir or clank or hum. Its movements are glacial, its mirror adjustments measured in nanometers, its rotation so slow that watching it reposition would be like watching the hour hand on a clock. And yet, in that stillness, it is performing an act of extraordinary violence against human ignorance, peeling back layer after layer of assumption with the patient insistence of water wearing through stone. You have been with it tonight, in a manner of speaking. You have drifted through the deep field and seen galaxies that should not exist at the sizes and ages they present themselves. You have sat with the Hubble tension, that stubborn numerical disagreement that refuses to resolve, and felt the quiet alarm of realizing that two trusted methods of measuring the universe cannot agree on how fast it is flying apart. You have considered the possibility that dark energy, the dominant component of everything that exists, might be changing its behavior in ways that alter the ultimate fate of the cosmos. You've visited ghost galaxies stripped of their dark matter, and monstrous black holes that gorge themselves into enormity before the universe had time to set the table properly. You have peered through the atmospheres of alien worlds, hoping for the chemical signature of life, and finding instead a complicated mixture of ambiguity and absence. You have learned that the early universe was chemically richer than it had any right to be, flooding its first galaxies with heavy elements at a pace that suggests the cosmic dawn was far more explosive than the gentle sunrise the models depicted. And you have sat with the silence, the vast, deep, unbroken silence of a universe that may or may not contain other minds, but has so far offered no evidence that it does. All of this was found by a telescope that almost was not built. Remember that. 4 near cancellations, 25 years of development, a budget that ballooned tenfold, congressional hearings where legislators questioned whether the science was worth the cost, a question that scientists answered with projections and promises that have now been exceeded in every measurable way. Webb was a gamble, and the gamble paid off. Not because it told us what we wanted to hear, but because it told us what we needed to know, which is that we do not know nearly as much as we thought we did. There is a fringe but delightful idea that circulates in certain philosophical corners of the astrophysics community. The notion that the universe becomes more complex in response to being observed, that the act of looking forces it to reveal layers that would otherwise remain hidden. This is not a serious physical proposal. It is more of a metaphor, a way of expressing the experience of discovery as a dialogue rather than an extraction. But it captures something true about Webb's mission. Every observation changes not just what we know, but what we know we do not know. And that second category, the known unknowns, has expanded enormously since those first images arrived in July 2022. Scholars still argue about the long-term legacy of the James Webb Space Telescope. Some believe it will be remembered as the instrument that precipitated a revolution in cosmology, the tool that forced the field to abandon lambda CDM and construct something better. Others believe the model will survive with modifications, absorbing Webb's surprises the way it has absorbed previous challenges, bending without breaking. The truth is probably somewhere in between, and it will take decades to resolve, because scientific revolutions are not events. They're processes, slow and messy and full of arguments, that generate more heat than light before eventually grudgingly producing clarity. What is not in dispute is that Webb has changed the conversation. Before Webb, cosmology felt like a field in its mature phase, polishing a well-established framework, filling in details, refining decimal places. After Webb, cosmology feels young again, full of questions that do not have answers, and answers that do not have explanations. That rejuvenation is a gift, even when it comes wrapped in discomfort, because a science that has stopped being surprised has stopped being science. And now the telescope continues its work. Tonight, while you have been lying here, Webb has been collecting photons. Some of those photons left their sources when the universe was a fraction of its current age. Some travelled for 13 billion years across expanding space, dodging dust clouds and gravitational wells, red-shifting slowly from visible light into infrared, until they arrived at a point 1.5 million kilometres from Earth and landed on a golden mirror the size of a tennis court, where they were focused, filtered, and converted into data that will eventually appear on a scientist's screen as a spectrum or an image or a number that does not match the prediction. And when that number does not match, someone will lean forward and the frontier will expand by another inch, and the universe will become a little more itself and a little less the story we told about it. That is what scientists were afraid of, not any single finding, not any particular galaxy or black hole or exoplanet or chemical anomaly. They were afraid of being wrong at the foundations, and Webb has gently, persistently, beautifully confirmed that they might be. The fear is productive. The fear is where science lives. And tonight, from your warm, safe, gravity-bound bed, you have been living there too. Now let the images soften. Let the galaxies blur into gentle points of light, no different from the glow of a nightlight in a quiet hallway. The black holes are far away. The tensions and anomalies and unanswered questions will still be there in the morning, patient as starlight, waiting for someone to look at them again. But not you. Not right now. Right now, the only thing expanding is the warmth of your blanket, and the only redshift is the slow, sleepy drift of your thoughts as they stretch and fade towards something quieter. The universe is vast and strange and full of things that do not yet have names, but your room is small and familiar and full of things that do. The hum of the fan, the weight of the covers, the steady rhythm of your own breathing, which is, when you think about it, a kind of rhythm the universe taught carbon and oxygen and nitrogen to make long ago in the heart of a star that no longer exists. You are stardust listening to a story about starlight, and both the dust and the light are very, very old and very, very tired and ready at last to rest. Sweet dreams,